Cool. And check to make sure. Cool. Here we go. Hey, Matthew. How are you? Good to hear.
Okay.
Just wait for the okay from soon. Well, we're actually we'll have 3 minutes. How's the live stream?
It's running.
Okay.
So I have an announcement.
If you have a Apple style adapter, that would be good.
What is
So we aren't able to plug into the audio system because Apple adapters have that extra mic pin. Otherwise, we're just gonna have to keep using the.
Okay, cool. It was okay, wasn't it?
They could do it. It wasn't the best. They can. If we can't do better, then we can't do better.
I don't know if we can, but
So, all right.
Next year we'll make sure we'll have the adapters.
yep. Making it on your list.
Yeah, I figured it out. Let's be proactive.
Here we should go.
Hello? Hi. Just before we get started with the next talk, I have an announcement. I'm here at the moment representing PLT Design Incorporated, which is a real company, and we like to hand out shares in that company. As Robbie likes to say, the monetary value of our company is doubled every year. It was $0 last year, and it is twice that this year. We expect to continue on that path. So this is, even though it's a real thing, largely symbolic, but we like to recognize people who have made significant long-term contributions to Racket, to the Racket community. And so this year, we are adding Neil Van Dyke, so 10 chairs in PLT Design Incorporated for Neil. I don't think he's here, but maybe he'll see this on video or recorded. So let's give Neil a hand.
Okay, good afternoon. How many people were in Strange Loop before this? Okay, so during Strange Loop, I was playing kind of an imaginary drinking game, which is that every time someone mentioned one of the decades from 1930 through 1970, you would have to take a drink. And so, I mean, that could be a non-alcoholic drink, or it could be bingo or something, but there are a lot of mentions of the ancient times of computer science. So for this session, for RacketCon, I'm proposing a different drinking game, which is based on the phrases PhD student, Indiana University, and Sam Tobin Hochstadt. So just remember that. So this next session is about infrastructure, and music and poetry programming has interesting technical challenges as well as beauty and elegance. I think that infrastructure has some beauty and elegance as well as interesting technical challenges, and that is our topic for this next session. And with that, I would like to introduce Andrew Kent, who is a PhD student at Indiana University. Sam Tobin Hochstadt.
Thank you, everybody. It's great to be here in front of you guys today. And I will be talking today about an extension we've been working on for TypeRacket. And it's something we've tested and would like to tell you about, and we hope to get it to you pretty soon. So it's a practical, dependently typed racket. And we feel that this is it's a natural kind of next step in the kind of program specification that you can get by adding TypeRacket to your Racket programs today. And it's maybe one step beyond that. So let's start off by talking about a story. We're going to motivate this with a story. So once upon a time, we had a developer, and this developer was sitting down at their computer, and they had a revolutionary game idea come into their head. Now, I know none of you read user agreements, but you've already agreed to not steal this idea from me, so I'm just... So the idea is he's got to pop up on Racket, and he's got this little guy that he's going to have on the screen, okay? We're going to have these levels, and we're going to be going around trying to eat these green dots. And while he's running around trying to grab these, there are these nefarious individuals tracking him on the level that he's trying to avoid. So we think this is going to be just absolutely phenomenal. We're going to call it Rackman. And so we've got our, we started developing, we're starting to create some different modules for the various features and parts of our program. And after a little bit of time, we put this on GitHub and we've got some users, right? Things are going great. Then we start to get some new ideas, some features, right? Maybe some pull requests for some of these people or others, and some ideas and things. So we're really getting some momentum behind this project building, right? And so after a while, we get quite a large user base. So this is turning into a pretty popular idea. I mean, obviously, we can't just leave it as it is now. So we start to add features and make changes to these modules and these things, and even start to add new modules that are going to be interacting with these features. And things are great, but after a while, things get a little bit tumultuous. We start getting bugs creeping up all across the program, and they're quite difficult to keep at bay. They just seem to be creeping up all over the place. And what happened in this particular case was that we kind of built up a little bit of technical debt. We sprinted ahead doing all this awesome development, but maybe we didn't think it out enough. We didn't lay things out. And so maybe we've got some spaghetti code that we need to refactor. Maybe we've got some additional testing that we didn't do. And among all these things that we can be doing to try to fix this problem and get us towards a good, stable game, one thing we probably want to do or want to look into doing is making the specification for these various parts of our program more explicit and actually enforced. And so Racket is there to help us do that, right? We're not on our own doing this. So what are the ways in Racket that we can enforce specifications and invariants? Well, there's a lot of options, as with most things in Racket. So we can do the time-old tradition of just throwing assertions directly in our code, right? So in your thing, unless some invariant is met, we throw an error. We also have Racket's contract system. So if we don't want to be mucking up with all this error checking code, we could take our functions, and as we provide them to other users of our module, we can wrap those in a contract that will be checked on the input and output of these functions. So it's going to be enforcing that specification. And then finally, we also have typed Racket, which we'd heard a little bit about today, that allows us to add some static compile time specification to our program. So let's talk about a particular part of this game that we're imagining. Maybe there's a render function, okay? And this function takes a vector of sprites and of locations to draw them to the screen, perhaps. And so this is just a really basic, we're looping I, the index variable, from 0 to 1 less than the vector length. And we're going to draw each of those sprites in order. And so we're using typed Racket, so we want to be statically enforcing some things about this. And so we give it the type that you would kind of expect. Okay, it takes in 2 vectors of the appropriate values, and this one is causing an effect, so its return type is void. And so when we get call sites that are kind of breaking this, that aren't meeting this type when they're calling, they're passing a list there, we get static errors, and this is great, right? We get that immediate reporting. Dr. Racket does a great job of helping out these things. But unfortunately, if we have another site where we are passing 2 vectors, but the length of one is not long enough, right? We're not going to draw that third bad guy. That's not going to be caught by the type checker today. And I mean, obviously there's limits, but that seems pretty simple. We'd like to handle that. And so what we're going to do is take this type of render, and we're going to mess with it a little bit. So we're going to make it a dependent type. So I'm using the squiggly arrow. You see that change there for these. And so we'll kind of shuffle things around. We're going to add an ability to name the arguments so that we can refer to them. And then instead of just any vector of locations, we want a vector of locations that meets some particular refinement. And we're going to throw in a logical proposition. So it's any vector of locations that meets this fact, this logical proposition. Now, a logical proposition, I've never heard of this. Maybe you're thinking you've been using typed Racket. And so if you were in Dr. Racket and you entered number at the REPL, you would get the type. And what's this funny thing over here? Well, this is a proposition right there. It's telling you if we return a truthy value, a non-false value, the argument was a number. Otherwise, it was not a number. You may have heard these called. I want you to forget this word the minute I say it. Filters. Sometimes people call them those, but they are logical propositions. You can have conjunctions, disjunctions, the wonderful things that you can see in other areas as well. And so we'll use the logical proposition that the length of these vectors we have to get is the same as the first argument. So they need to be equal in length. And so if we had this type on it, when we go to have a call site where we're passing 2 vectors that are the same length, we get a static type error. Now, we have this type, which is giving us a more detailed specification for what's going on with this function. We pushed a little bit more about what's required into the type. And so with that, can we do anything with the body of this function? Well, there's something that's pretty obvious in situations like this. The vector ref that you see here, this does a dynamic check. So you give it a vector, and then you give it an index. And when you go to reach into that, it's testing at runtime to make sure that that's actually a valid index for that vector. In this case, we know that because of the way this is constructed, right, we're in a for loop bias going from 0 to 1 less than, these are all going to be valid. So maybe we're tempted from here, we're going to manually put in these unsafe vector ref calls. These are perhaps analogous to like a C array reference. There's no checking, we just reach into memory and we pull something out. I think that's akin though to maybe instead of unsafe vector ref, let's just put little bombs in our program that may or may not go off in the future. And then off to the side, we can have a little stopwatch so that we're not allowed to know how much time is left. And then later our program can change and explode, right? So let's not do that. Let's rewind, and instead of unsafe vector ref, we want to use a safe vector ref. Now what on earth is that, right? Wasn't that the first thing? So safe vector ref, we're going to take vector ref, which takes vectors of things, an integer, and then it gives you one of those things back, right? And we're going to add some detail to that, just like we did before. So safe vector ref, you have to give it an integer where the refining logical proposition there is that it's greater than or equal to 0 and less than the length of the vector. So that's what we're going to use as the type for safe vector ref. And what is our definition going to look like? Well, we'll just use them, safe vector ref, since it's doing the quicker check anyway. But now, with that type, we can statically guarantee the safety of usages of that, instead of the waiting for perhaps something to happen bad in the future that we don't know about. And so we have our function here now, and so I've kind of illustrated this through drawing an example, but if we were to just say, what have we added to type bracket to do this? Well, we've added dependent function types to the function types that are allowed. So now we can have functions that explicitly name their arguments, just like some of the dependent contracts we saw in Matthias's talk earlier, and then we can talk about those in the types. We've added refinement types, and these are the things that allow a type to have a dependency on some other value like that. And then we've added new propositions. So we already had propositions that things are or are not a type, ands and ors, and we've added linear inequalities over things that are an integer type to that. And then what is this bias? Well, as we saw, we get more detailed specifications. We can remove safely things like integer bounds checks if we wish. And you can use these same tools in expressiveness. People have shown how to make red lat trees, where those static invariants about the data structures, because they can all be expressed with the tools that we have, integer relations and things, you can use those as well to make a dependently typed red black tree. And another nice thing about this extension is we haven't done this in a way where the fact that we're allowing you to have any integer statements like this, it's not like fundamental to this edition. So what this edition is amicable to in the future if there are additional theories that people would like to be able to start writing propositions about because it's a decidable nice tool. We can do that with the way that this is set up. Now, there's this question when we're looking at a extension like this, and that is, we're adding this new expressiveness, but is this going to be a infectious addition? And this is actually a question Matthias asked Stephanie Wyrick, I think at ICFP 2014 or thereabouts. And I thought it was a great question, right? Are we going to get into a situation where we've got a user, and this was the type of render, the original type, and they've got, everything's working fine. Things are type checking, they're calling it on A and B. And then when we go to enrich the type of render, and we give it that more specific type, all of a sudden that doesn't type check anymore, right? We get an error. And maybe it was good. Maybe that was a place in the code where we really weren't sure they were going to be the same length, but maybe it was. We knew they were the same length, but the type checker just wasn't able to figure that out. Well, we can just throw a dynamic check in, unless these are of equal length, then throw an error. And by adding this, we do get this to type check. So if there are cases like this and you want to add that, that's great. There's a little bit of flexibility there. But if throughout our program we have lots of those little red highlightings going on, and we end up kind of throwing these checks everywhere, that's obviously not a good thing. Our goal isn't to use stronger types and then manually inject that dynamic checking everywhere in our program so that we can satisfy that. And so maybe, in some cases it's going to work great, and in others there's going to be a little bit of a give and take, and you're going to be able to decide whether you want that or not. And here, perhaps, we're not ready for that. So the nice thing with this approach is that dynamic check, what we can do, we can get rid of the proposition about them being equal if our program is just struggling to have that be obvious at each usage point. We can go back to the old type. And that second vector ref there isn't type checking. Well, we can just throw in maybe a error check that we maybe should have had originally anyways to the beginning of this function, and that will type check. And so instead of having that everywhere, we can start out with it here and then experiment with that. And so the flexibility that this allows to work well with runtime tests, just like TypedRacket does when it's reasoning about the types of values, it kind of allows you to have it your way with how specific you want types to be in different areas. Now, I think another question that's important to ask, the dependent types are kind of a hot topic right now, right? There's a lot of research going in, there's a lot of exciting, awesome systems, and so we've demonstrated a few things here, but is this really dependent types, perhaps you're wondering? You know, some people, they're very fond of the true Scotsman style of arguments, you know, and they're thinking, well, a true dependently typed language can, and then they've got some satisfying condition here, you know, that we can fully type quicksort, or we can type check printf, or we can, you know, we can do theorem proving when we need to, you know. Your program couldn't tell you, but you should be able to get in there and add a theorem proof if that's the case. I mean, those are all awesome things. I'm not ragging on those. But so what we have done, we can't do a lot of those things that I just listed, but we have enabled you to start encoding some of those dependencies in types with this extension. What we've not enabled you to do, though, so this is a little cock example. So this is a definition of quicksort that's actually kind of cool. It takes in a list. It says that it is known to terminate because the length of the recursive calls of the list is going to shrink. And the return value, instead of just being a list, is a list of naturals that is sorted and is actually a permutation of the original thing, right? So you can do some amazing things with dependent types. But the problem, or some of the difficulties that people are still flushing out in a lot of these cases, is that this particular example, as I was toying around with this in Coq, led to some, you know, it did not type check on its own. It immediately said, okay, well, we've proven some of the obligations, but now we need to start proving these additional things that we couldn't, the type checker itself couldn't prove to be the case. And so at the moment, you know, we're not tackling things like that. We're trying to just have natural extensions that allow additional things to be added without explicit, you know, theorem proving going on as well. Now, this is not Vera Racket, that idea that we heard Matthias talk about that perhaps someday we'll get to see. And so, so finally, you know, when can we start using some of these things and experimenting? Well, soon. Non-answer answer. So we have prototyped this extension. So we've taken these ideas and embedded them in the entirety of typed Racket, and we've confirmed that, you know, with the right design, that this works well with the way that typed Racket is currently doing things, both in an implementation and in a user sense, we feel. And we run, we took this prototype and we ran it on about 57,000 lines of code to see if vector accesses in general, how often we could statically guarantee that they're going to be safe. We hit about 50% on that mark, and that was without any changes to the code bases. So we confirmed that it can work well. We have a map for how we're going to add this to typed Racket laid out. And it would be great. I think a good target to aim for is implemented by this Christmas, 2015. And if not fully implemented, definitely a significant chunk of the steps and features to be there shouldn't be there. If you wanted to poke around at some of the details, if you're interested in how typed Racket is implemented, you can look at what this extension did to get these things to work. And thank you for your time.
Great, that was excellent. If you want to unhook your computer while you're taking questions, you can let the next person get started. And speaking of questions, yes, why don't I do your microphone? Why don't I do my job properly? Thank you very much.
So that was really cool. There were two decisions you made that surprised me a bit. So one is that when you're giving the dependent function type, you had bindings for all the variables, and then when you had refinement, it had a binding again. So one might expect that you could shortcut that and just do one binding. And, you know, that's a low-level issue, but may be important for practical use.
Absolutely. Yeah, I was trying to keep with the kind of minimal, here's what we're adding and what it gives you, but absolutely in practice, there would be some redundancies if we didn't add some additional sugar on top of that. So yeah.
So you're planning on dealing with that, right?
Yes, yes.
And then the other thing is you pointed out quite recently, well, we're not doing verification. And it makes sense, of course, to go slowly, but it doesn't seem that hard to just add hooks for that. So why aren't you doing it? What is hard about it? Why is it not worth doing in the first instance?
Well, so we're not doing it in this next semester that has already started, where we will be implementing this. But I don't mean to make any claims about in the future it not being done.
But the question is, the question is,
Pull request accepted.
Why
That's
is
the,
it's actually checking the proofs coming out, but just having hooks in there that let you put in simple proofs and then allowing more and more complicated ones. Doesn't seem that hard, but did you leave it out because it is hard in some way that I'm not seeing?
no, I don't have any knowledge that that would be particularly impossible to do, and we omitted it because of that. We just haven't looked at it yet.
Okay.
Hey, any other questions? I see one up here at the front here. He's the master of the NES Chamber Orchestra.
Do you write your own linear inequality solver, and did you require for theory?
We just use a simple implementation of the 4D Motzkin illumination method, so we just use our own implementation of a nice, simple, tractable one. So in the future, we could explore other ones or maybe off-the-shelf ones and see if they do a better job, but right now, that's what we're using.
And require for theory?
Right.
Okay, I think time for one more question. I don't know if we should take a question from this individual, but.
Do you guys see that you use to get another syntax for dependent stuff?
I'm trying to not commit to any one particular, so. If you
Well,
see
we
something-
already have one. Why are you not using the one that exists?
Which one?
The indie contract.
LOI.
Well, types don't look like contracts right now.
They do, assumably that Sam's mess over last year.
Got it.
Thank you.
Thank you for that insightful question. All right. Our next speaker will be talking about just-in-time compilation strategies, I believe. And I asked him for amusing and preferably embarrassing anecdotes to share, but he was unwilling to share them. So as soon as the microphone is ready, are you ready?
I think so.
Excellent. Okay, so you will be shocked to hear that this next speaker is a PhD student at Indiana University. Spencer Bauman.
Thank you for that introduction. So I'm going to talk a little bit about a new tracing JIT compiler for Racket that we've been working on at Indiana University, but also with some of our colleagues at King's College London and the Hasso-Plattner Institute. So Racket already has a JIT, per se, but let's start out with a motivating example to see what's wrong with kind of the current situation. So here's a simple definition of our dot product function. We even added some context in there to make it nice and safe. Unfortunately, it's not particularly fast. It takes about 9 seconds to run on the sample data that I cooked up. Now, the first thing we want to do if we want to make it run a little faster is we can subtract out the contracts, right? So that safety has a pretty significant runtime cost in this case. So we subtract those out, we're about 2.5 times faster. If we want to get yet faster still, we have to do some manual specialization and do the work of the compiler for us. We specialize some of the for-sum construct and some of the arithmetic, and we're again about 3.5 times faster. But if we want to get as fast as we can out of Racket, we have to drop down and write parenthesis-based C, basically. So this is what our fastest dot product implementation looks like running through Racket. We're now significantly faster, about 33 times faster than the original implementation. Unfortunately, we've had to brutalize our function pretty significantly, and that's kind of unfortunate when you're working in the second best programming language. So we developed Picket, which is a new tracing JIT compiler designed to kind of deal with this issue of the same Racket times. Not only are we significantly faster in every case, but the difference between our fastest and slowest version is only about 20%, rather than 0.3%. So, at a high level, the idea is we want to apply modern dynamic language JIT compilation techniques, as opposed to what Racket currently does, which is basically ahead of time optimizations plus some lazy code generation. And to do this, we make use of some existing work that comes from the RPython project. And this is a project that came out of the development of Python. It's a language and framework for implementing efficient dynamic language interpreters, most notable for its inclusion of a fast JIT compiler that you can take advantage of simply by writing an interpreter for your language. So a little bit about the high-level design first. So we didn't want to go through the trouble of implementing things like Racket's macro expander ourselves because we think that's not particularly fun. So instead what we do is we bootstrap a functioning program making use of the existing Racket macro expander. So when we want to run a program, we first fire up a Racket, a separate Racket process, which runs a little script we have, and that in itself invokes Racket's macro expander and gets us down to Racket's core forms, which is a relatively minimal AST representation of our program. From there, we serialize that out to disk via JSON format and read that in on the Picket side, doing some relatively minor cosmetic modifications to make our lives easier. And that AST is what the interpreter operates on. There is no subsequent bytecode compilation as is typical with high-performance dynamic language VMs. Instead, what we do is we feed that into the CDK machine, which was nicely developed for us by Matthias. And it's typically used to specify the semantics of the lambda calculus. Instead, what we did is we scale it up to work on all of Racket's core forms, and we just feed the resulting Racket programming. So the kind of high-level way this works is we have this step function which takes an expression, an environment, and a continuation, and it steps the program one evaluation step, producing a new expression, environment, and continuation. And this has a couple notable advantages. The CDK machine, by construction, implements proper tail calls. And since we're already manually managing this continuation term, implementing high-level control features like call CC is relatively straightforward. So, and that's the full structure of the interpreter. I'd like to talk a little bit about the compilation strategy that we make use of here, because it's significantly different from what most JIT compilers use these days. And it's what's known as trace compilation. So rather than doing kind of iterative transformations on the AST to work your way down to low-level machine code, trace compilation works by kind of instrumenting the dispatch loop of your interpreter. This is typically done in a bytecode interpreter setting, such that after you execute each bytecode, one per iteration, what you do is you record into some buffer a sequence of instructions which emulates what the interpreter just did. So if you just did your multiplication bytecode operation and both of its arguments were floating point values, well, you emit a sequence of instructions that emulates floating point multiplication. And during interpretation, you continue to record these until your buffer fills up, at which point you shift this buffer off to your compiler, generate code for that path that you recorded through your program, and when you reach the point in your program again that initiated this recording process, you just jump to that piece of code. With the caveat that if control flow should ever bail out or should ever diverge from what you just recorded, you need to bail back to the interpreter until you can generate code for those subsequent execution paths as well. And eventually you will end up completely fleshing out all of the relevant paths through your code. But doing all that instrumentation and implementing all of that compilation framework is a lot of work still. Instead, we make use of the existing JIT that comes with our Python, which is what is known as a meta-tracing JIT compiler. This is how it manages to be language agnostic. The idea is it operates one level up from a standard tracing JIT compiler. So instead of recording operations as they're performed by your source code, instead what it does is it observes the execution of the interpreter you just wrote and records the operations performed in the interpreter. So now, simply by observing the interpreter, you're now compiling the language that you're interpreting. And obviously, you have to provide enough hints so that the JIT can properly optimize the resulting code and remove the interpretation overhead. So we take that process and we apply it to the dot product function that we saw in the intro, And this doesn't really matter which version. The code generated is largely the same. And so it has these two, starts up with these two guard expressions, which just make sure we have not run off the end of either of our input arrays. Two array fetches to get the next item at each, at the current index. You multiply those together, add it to the accumulator, and you just increment your two loop counters. So we have one counter for indexing into each array, and then you just jump back up to the top. And this is pretty close to what you would want out of a C compiler generating a dot product function, right? You're operating over unboxed arrays of floating point values and doing arithmetic without any extra interpretation of it. This is how we managed to get so much faster than Racket on those particular examples. But this is a research project consisting of only about 14,000 lines of Python code. How much of Racket can we actually implement in that small amount of code with that little human resources? And the answer is a surprisingly large amount. This is where implementing Picket as a CDK machine comes in real handy, because it's a very high-level implementation. So we have functioning file I/O. Since we need to run all of these benchmarks and show up how fast we are, we obviously have to implement the full numeric tower. We support Racket's contract system, including some of the more advanced features baked into Racket's runtime, like impersonators and chaperones. Since we support that, it's not too difficult to go from there to supporting typed Racket. And just to give you an idea of the remainder, there are a lot of primitive functions baked into Racket's runtime, about 1,400 of them. Of those, Picket implements about 900. Granted, those 900 are the ones we most need to run benchmarks, but it still gives you kind of an idea of how much work is left to be done. There are a bunch of things that don't work or will be difficult to implement just due to the architecture we've chosen. Implementing the FFI will take some, probably be time-consuming and error-prone to map everything to the equivalent R Python constructs. We don't support Scribble. Anything that requires a GUI or network access is currently not supported. As of yet, we have not implemented threads, though there is some, we are looking into a green thread implementation that will at least allow us to execute examples which make use of threads. And obviously, those 500 remaining primitives would be something that we would like to implement at some point. So the dot product example made things appear very rosy. We were significantly faster than Racket, and the story isn't always that good. We've inherited some of the well-known performance edge cases that tracing JIT compilers have, which is anything with very branchy, irregular control flow, code that isn't easily expressed as a loop. Trace compilation is based around compiling loops. If things don't actually look like a loop, we're not going to do particularly well. The canonical example is anything that looks like an interpreter, something with one loop that has hundreds of cases dispatching to various handler functions is typically a bad performance spot for tracing JITs. But anything that fits into straight loops or numerical computation, we're excellent at. We definitely win at least all the numerical benchmarks. And so, as you can see, we've got two benchmark suites here. One is the Larceny benchmark suite, which is about 50 benchmarks. They run on a variety of systems, so we compare Racket and Picket, but also Larceny, Gambit, and Bigloo, which are 3 ahead-of-time optimizing compilers, all fairly effective at what they do. So, and then we just take the geometric mean across all 50 to boil it down to a single number for comparison here. As you can see, Racket is the slowest by a fairly significant margin, with the next 3 being the ahead-of-time compilers. But significantly faster still is Picket, clocking in a little over 2x faster than Racket. And similarly, we took the Racket entries for the programming language shootout benchmarks, and again, Picket ends up being about 2x faster, with the caveat that these are ones you would expect Racket to do as well as possible, and these ones have gone through the manual specialization process that we did to that dot product function. So this is kind of the optimal case for Racket. But it's useful as a point of comparison because we can get an idea of how dependent Pickett is on this manual specialization process as well. So what we can do is we can take those shootout benchmarks, manually despecialize them, inserting more generic arithmetic operations, safer forms of operations like vector ref. And when we do this, Racket slows down by about 30%, whereas Pickett only takes about a 6% performance error. So since we're already significantly faster than Racket, it's fairly safe to conclude that we're also much less dependent on the specialization process to get anywhere near that good performance. So a little bit of future work, things we're looking into, or things we would like to improve. We do currently implement impersonators and chaperones, and generally across the board, we outperform Racket on programs that make use of impersonators and chaperones. But we're looking into ways to slim them down further and expose more of their structure to the JIT compiler so that we can get even better performance and hopefully significantly less memory usage. We're also looking into exploring the interaction between the ahead of time optimizations that are currently performed by Racket and those that are performed just in time by the RPython JIT. Currently, we cannot take advantage of the ahead of time optimizations because we operate on Racket's core forms rather than its bytecode representation, which is what Racket's optimizer operates on. So we're looking into pushing that later on and interpreting something later down the compilation pipeline. As I said before, we want to implement green threads, in particular to explore optimizing inter-thread communication and scheduling patterns to kind of expose that to the JIT and optimize away thread boundaries. And obviously, improve performance on complicated control flow, which is really the worst case for Pickett. Because of Pickett's architecture, it takes a particularly large hit on programs like this. And obviously, we would just like to support more of that. That's all I've got. Thank you for listening.
Great, that was excellent. We have time for one, maybe two questions. So, Jim.
Can you talk more about examples where it performs poorly? So you said complicated control flow. So for instance, with the standard scheme benchmarks, is the Boyer-Moore one of those that you don't perform well on, or do you do well in that? Can you go in when you don't do as, is it that you don't do as well, or you actually are beaten by Racket?
So there are definitely cases where we get beaten by Racket. These end up being pathological cases where if we don't optimize well, the resulting assembly code basically ends up simulating the CFA machine stack. It's sometimes difficult to reason about which examples those will be. Small changes can have pretty significant impact on how effective the JIT is, but there are definitely examples in the large scheme benchmark suite, for example, where we're 2x slower than Racket.
Like, what about Boyer-Moore? That's just one that I think of off the top of my head that seems like you would perform poorly at.
So the Boyer-Moore is actually an interesting example because we have a couple versions of Pickett floating around, and there are some where we do significantly better than Racket, and a couple where we do significantly worse. So it's a little schizophrenic.
Great, okay, I think we should probably move on now. If you have more questions, all of our speakers will be available later. So next, someone who is not a PhD student. I think our next speaker.
Positions are still open.
I think our next speaker needs no introduction. I think Matthew Flatt, everyone knows him for his immense contributions as the author of dozens of posts explaining why the top level is hopeless. And he has also done some work on Racket. No, but seriously, if Matthew Flatt says that something is hopeless, then I believe it's hopeless, because I've seen no one who's more willing to take on a very difficult problem and stick at it until he finds some solution. And the latest example of that is Matthew deciding to take the macro expander and Racket, rip it completely apart, and put it back together again, and talk about it for us today. Matthew Flatt.
All right, so as Greg says, there is a new macro expander coming in the next version of Racket, so released in a month or so. For most programs, this is a pretty small bend in the road. Most macros will still work. If you try to use submodules and type bracket, they'll finally behave more like they should. There are some macros that will not work well, particularly if you have a macro that expands to a submodule, and I'll say a little bit more about that. Performance is about the same, memory use is about the same. The size of the implementation, if you just count lines, it's pretty similar, although I think it's better code now. So why am I so excited about it anyway? I really have to explain what I mean by macro expander to get at that. And this bit is a little bit redundant with Matthias's talk. It's a little bit in conflict with his talk because I call it a macro expander. But what I mean is a lot more than just define syntaxual. Right? So you've got a module here. I'm sure you recognize this module sitting out in the field immediately. It's implemented in the language #type bracket. And to talk about what the expander means to me, we're going to have to sort of go underground and see what's going on here. So let's crawl under there. And what we see is this program is being pulled apart, and bits of the program are being sent off somewhere else. So that's the job of the macro expander, to sort of break the program down into fragments of the program and send them off somewhere else. We'll just get rid of the ground because it's in the way here. In the case of #type bracket, of course, it goes off to the type bracket compiler. So it receives these representations of the program, and it looks at them and tells you that your program is well typed or it's not. And if it is well typed, then it will also work with another little compiler for contracts, which takes some of the same fragments or some that type bracket synthesizes, and it puts those together into generating some regular old bracket code, untyped bracket code. As those type bracket, those pieces flow in. So somehow these different fragments of the program need to make sense when put back together, and then those get shipped off to the Racket compiler, and maybe it's combined with some other module that's in Racket, and so on. And well, of course, you know that type bracket, I've drawn it as a factory here, but it's really just another program. It has to be pulled apart and compiled through Racket and so on. So you end up with, this is what the world looks like to me, right? All of these fragments of programs flying around between different pieces of our ecosystem, and all of those fragments need to make sense. And well, there's more, so I'll just throw in a few more here. Right? It's the job of the macro expander to get these pieces in the right places and to make them understandable to those pieces, to make them make sense and be put back together again. And well, none of this is new, right? This, as Matthias was saying, was where we've been, and it's worked out very well for us. Oh, see, this is actually a picture of the old macro expander. And you see it's lost a little fragment here. I bet that was a submodule in type bracket. And you know, what's going on is we sort of built this system at the same time as we were figuring out what it was supposed to do. And it was getting kind of pushed to its limits, and that pipe there is starting to break. And the repair has turned out to be not so much fixing the pipes, but looking at what is a fragment of a program, right? How do we represent that? You know, there's been a model around that we built on that's great, has worked well for us, but the places where the system was starting to get creaky had a lot to do with this having to reason about these things, because sure, it's an identifier like X, but then as these things flow around, they sort of change colors so that we can kind of track where they came from, except as they flow into other places, they get renamed, and then maybe they change color again, and then maybe they get renamed, and that doesn't look all so bad. But then some things want to say, well, it wasn't actually an X, it was actually get X. So pretend it was get X from the beginning. So we have to keep the history of all of those transformations around. And this is what a macro implementer has sometimes had to hold in his head. And well, that's, you know, it was okay, it was workable, but it wasn't great. So we want something easier to think about than these cycles and epicycles and so on. So we're going to go back and say, this is what the talk is actually about. You know, what is a better representation for these fragments of syntax? And the motivation is to make it work in this whole big world of cooperating languages and modules and so on. But of course, we can just go into one particular module because you can have local defined macros, and but we can look at the problems there, and it turns out that that will let us talk about the problems that exist everywhere. So I'm going to pause those flying spheres and go over here. So let's look at some actual bits of code. So define x ... Something happens in the dots there. What I'm doing there is computing a value that sort of counts as a pre-made value that I'm going to use in other places in this module, unless x is false, and then I'll do some other work. So you might say, why not call it pre-made instead of x? I'm just not going to be very creative with variable names. That's all. So because I'm going to do this often, either use this pre-made variable, pre-made value, or evaluate some expression, of course, I'll write the macro, pre-made or. And it just says either x, or if x is false, then go do this. And it's a macro instead of a function because the work that I need to do, if the pre-made value is not there, may be a lot of work, and so I don't want to do it at all. And I'm sort of just making a macro to delay the evaluation there until I need it. And then here's a use of it. I let x be some function to do a lot of work to compute a value, and then I use pre-made or to either get this x or call the x function to get the result. Okay, and you can see why I've been so uncreative with my variable name. It's to simulate the collisions that are inevitable in the larger picture, right? I can simulate them by using x all the time. So what should happen? Pre-made or is a macro indication. Right? So we're going to match it up with this definition of pre-made or. That parenthesized x gets matched up with e in the pattern. And so where e appears in the template, it's going to come out as a replacement for the use of pre-made or. Meanwhile, the or and x, they are not part of the pattern, so they will come down as is. I colored them orange here just so that we can remember those came from the macro expansion. It wasn't originally or and x there. And at this point, you can see a problem with the picture because this x still means the x that it should, but now I've got an x that is not supposed to be captured there. Right? This is one of the classic problems when you think about manipulating syntax. I meant for this x to refer to my pre-made x. And it's not that it should be the orange x because there are no orange x definitions, right? Still a blue x that it's supposed to match up with. It's not that I can treat x at the top level as somehow special because maybe this is not in the top level. Maybe this is in the definition context more nested in my program. You can write macros and macro uses anywhere. So they're the same kind of x. They're both local x's perhaps. And somehow I need to disambiguate this. And then, of course, we can do or is the classic macro example. I have the definition of or where I have chosen as my temporary name x. Then when I replace the use of or here with the macro extension, we get something that looks like this. I let x be the value of the orange x. If that's true, then I'll return it. Otherwise, I evaluate the function. And so again, I've got a different colored x. Here, I do have a green x, but then it's captured this other one, and so on. So that's the kind of problem that happens in the very small scale. And there are various solutions to this that involve those color changing spinning things. I want to suggest that what has really gone wrong with this picture is not that I've used the colors badly, but that I've sort of relied on a 2D representation of the syntax. Really a linear one, right? But 2D, and that I think of this x as being nested in there, because really, we see this 2D thing, but that x from the macro expansion is in a different plane than the code that it, at the place that it expanded into, right? So I want to break out into a different dimension somehow, and that's maybe more on the right track than thinking about radians. So that's the path I'm going to explore here, but let's sort of step back again. What is it that we know that works? You know, how does lexical scope work, and how does it fit into this picture? So here's again another program where I've used lots of x's, but for variety I've used a y also. What is the binding structure here? Even though it's a lot of x's, you can pretty quickly see that this x means that one, and this x means that one, and that one means that one. That's what we're used to in terms of you just look for the closest binding with the same name, and that's the one it refers to, right? No question there. There's another way to draw this picture, which I like a little more, especially for today, which is to sort of put a background behind the binding instance, and then put a background between the whole region where that instance lies. Okay, so it's the same sort of information. Again, this y binds to that y because it's on the same color, and this x, well, it looks like it's on a sort of light blue cyan, and that one's orange, but we know that the orange is meant to extend beyond all of it, right? So there are these different color planes, but in this case, in the case of lexical scope, it happens that they're all nested. Now, if I want to make this kind of picture, a flat picture, have that same information to let me know that X is really orange also, then I can write it this way. It's the same information. This says X is in the pink and the orange and the light blue areas. And I've left the contours there just to sort of remind you where they came from, but they're not really important for now. So you're with me? I'm taking this notion of binding scope and turning it into colors and a set of colors on each identifier. And what will I do with the OR macro? Well, those new pieces that come in, I will put a green background behind them. And you notice this let and this X don't have pink and orange and blue because it wasn't in those binding scopes. In other words, if we try to go back to this picture, it doesn't work anymore because you can't tell whether this green is inside the cyan. If I try to draw it in a 3D-ish way, then it's like these are nested, but this green came in at a different dimension altogether, and it's sort of orthogonal to those planes, right? And that's not going to be any better to think about. But if we represent it as these just sets of colors, we summarize that information, then it becomes something that's we can deal with, right? And notice also it's the colors that are in different dimensions, not the identifiers. This X is still nested in that let, and when I look at that binding, then I'll make up a new color for its binding. I will paint these things in purple, okay, because those identifiers really are there, and that's how this gets bound. Right, but at the same time, if I want to say what is the binding of this X, I need something that's compatible with pink, orange, light blue, and purple. This has a green, and I don't have a green, so I can't have been bound by that one. But this X is compatible with that one because it still has pink. Sorry, this one is the binding instance. But this one has pink and orange. That's more, even more compatible with it. Right? So there's a sort of subset relations on sets, not sort of, but exactly a subset relation on these sets of colors. And I want to, instead of finding something that's closest in some sort of 2D or linear version, I want to find something that's closest in terms of having the biggest subset of my current colors. Right? So, and then lexical scope turns out to be just a special case of that, where all the sets have a certain nesting structure. We can take this, oh, I should also mention that actually if the OR macro is in another module, then it doesn't really just have green because green was from the macro introduction. It also has that module color, which is blue, purple, let's call it brown. Brown, and that module would be the one that bound let. So even when I pick up this let, take it over into the other module, it still records that it came from some brown region where I might find a brown require that pulled that in from that. So that's the basic idea. We can double check our original main OR example. I painted it all blue now because it's all in some module. That's blue. So this X is the blue binding. This pre-main OR is the blue binding. And now I see a let, and here's a new X that I'm seeing. So I make up a new color for that and paint everything in the body of the let with that new color. So I got some pink attached to the blue pieces here. Now I get to pre-made OR. I see that it is bound by this pre-made OR binding here. It's compatible with the light blue binding. So that's still a macro indication. I still match up the X call with E. So it still comes back down that way. And then the parts that I introduced, the OR and the X, I make up some new color for them, orange like before. But now everything is okay when we look at this combination of the names and the colors. So light blue and pink is compatible with that, but not with this, so that means it doesn't capture. Whereas I still find this X here, which has a light blue color, which is compatible with the light blue and orange, and is in fact the most specific binding in this case. So you can push this through and try out more examples. There are some catches when it comes to definition context where you can both define and use macros, but the idea with some extra little rules about how you shuffle the sets around works out really quite a lot more easily than the same cases in the old way of doing things. So when you go read the new manual or you read write-ups about this, I don't call them colors, I just call these scopes. And so this set of colors becomes a set of scopes or a scope set. And then we still have syntax objects, but now a syntax object is simply defined as the datum part, which is a symbol or a list or whatever, combined with a set of scopes. And you can read more about this here. That's a long URL to write down, but if you just search for scope set Racket, I'm sure you'll find it. pieces of that are gradually moving into the manual as well. So we go back over here and continue. Then that means it's not perfect spheres floating around here. More specifically, it's identifiers, the sets of colors flying around, and they're flying around everywhere. And these sets of colors are basically the way that these different languages can cooperate and make sense of different fragments. That's sort of the public works view of things here. And that write-up that I pointed you to, one of its main audiences, other public works departments, right? Other languages that have macro systems or need macro systems. I think one of the obstacles for adopting Racket style or Racket scale macros has often been understanding this little core piece. And I'm hopeful that we have a better understanding and that will let more languages, more communities adopt it. But also, as always, we want you right on that main line, plugged into the plumbing there, so you can have fresh, hygienic macros right at your fingertips whenever you need. We're not all the way there yet, right? We haven't written the new macro system for dummies book or macros in 21 days, but maybe now that we have a better handle ourselves on how to reason about this, we can make all of this much more accessible. So, thank you.
Great. Well, we have time for questions, and unfortunately, I saw you first.
So can we have cool 3D animations for debugging macros, and can we use your animations for continuations?
I have not yet talked to Ryan about integrating the 3D view with the macro stepper feature. That sounds like a good plan. By the way, this uses Pic3D. If you haven't tried Pic3D, it's huge fun. But I don't see why we can't actually. My student Janchi, she's in here somewhere. Right, she's into debugging and visualization, so maybe we should pull some 3D stuff.
So I apologize in advance for not having read the poll, so this goes right up. But while you were going through the explanation, I think quite seemed to fit the model that you showed with basically what happens when you have something and it appears on the right-hand side of a defined syntax or less syntax. And that really kind of lunges your scope of information because really there's two different dimensions on which something can be the same as an identifier, right? You've got the pre-identifier equal and bound identifier equal. And I kind of really only see one dimension being represented there.
So first, a clarification on the question. Are you talking about recursive bindings at all, where you have like rect syntax, or?
No, just in general being on the right-hand side.
Just in general being on the right-hand side. So in the case of let, you see the blue, brown, I really do know my colors. Brown was the color chosen for this X binding, and you see brown was not added on the right-hand side. And that's what let does. It doesn't include the scope on the right-hand side.
Right.
If it were a let rect, then brown would show up over here.
I guess, no, I'm talking about as far as the difference between pre-identifiers and
okay, so going down to the free identifier, bound identifier. So what free identifier means is, with these two things, two identifiers refer to the same binding. And that's not a question you can ask independent of the set of bindings. So that's why in the implementation, in the description, there is a global binding table. So two things are free identifier equal when they have the same biggest subset match for a binding somewhere else. Bound identifier equal is simply they have the same sets. Because bound identifier equal means no matter which way you use one binding the other, one in a binding position, one in use, they would bind each other. So binding identifier equals even more straightforward. But overall, in the implementation, these turned out to be way simpler tests.
In your example, it looks like the thing that binds you is always a prefix, not just a subset, but a prefix of the colors of the thing being bound. Is that always the case or not always the case?
That is not always the case. It just happens in this simple example. Yeah. So if we had, well, let's see. Yeah, it's just not always the case. Is the way to say it.
Okay, I think we have time for one more question.
I think it's when you stash an identifier away and then pull it back later, which was always the complicated case that they can get out of order, and that's okay.
The way in which you found the one that matches, you said pick the one with the largest subset that matches.
Yes.
How do you know there aren't two?
Yes, there could be. That's why there's a new ambiguous binding error that you can get out of the macro scanning. And it's hard to provoke that error. You have to do things like stash the identifier away and pull it in. But there could indeed be ambiguity, and that is an error. And where I found that this showed up the most, as I was applying it to all our existing macros, is macros that were broken, that I just didn't have formally move them, try them out in the right context. But the ambiguous binding error tends to, for reasons that are not entirely clear to me yet, this is all sort of new, tends to expose problems in macros.
Does your paper write down an example of one of these ideas?
It does, yes. Yeah. But it's bigger than this, so that's very
Okay, well, I think we're at the point in our schedule where, well, first of all, a big thank you for Matthew Flatt. Okay, so it's about 3 o'clock. We have time for a half-hour break. I'm told there will be fresh coffee, and we'll see you back here at 3:30. Thank you.
And if you're speaking in the next session, please come up and test your laptop.
Yeah.
Tim, I have a suggestion for you. How do you make that converted a dependent penalty type function into a strict out and automatically generated the appropriate
So cast is that form. But maybe what you're thinking is that we could generate the type too.
Yes.
So I think that's true. You could generate a type that strips out all the refinements. So Ryan is pointing out that if you want to convert between the regular function, you sometimes only need to specify what the type of the regular function I think it's a good idea. I appreciate the suggestion. And take it there.
At first, I started like, but like, and the macro you give different colors. Are we switching or? Yeah, it's switching. I'll show you how to put things. Do you have a card slot? Do I have an SD card slot? There. I have. How much do you need? You can get Some of this is untied, but it's word I probably included below.
Yeah, well,
There's a
CLOS
new
gives
syntax.
you CLOS gives you a lot of like Racket is much more constrained. They're trade-offs.
Okay. Wait, what is it?
Syntax hyphen debug hyphen syntax object.
Okay.
And gives you a hash table, and one of them is bindings, and that is a list of colors. Of course, they're really just tokens.
Wait, so right now the background stepper does like expose that information, and it tells you what scopes they are, but it doesn't put them as colors. And if they were colors, then I could just see at a glance this one has a superset of this one, and this one has a subset of this one.
I'm not sure you can see it at a glance. There'll be little rainbows.
Yeah,
There are going to be so many.
Well,
There are going to be so many scopes.
yeah, if there are a lot of scopes, that might break it down.
But another thing is actually, usually the scopes are in the subsets really. There's never a green color. So you get to collapse those, and then things will have a small number of things.
But if there's an ambiguous binding,
And then it's an ambiguous binding. Those would either come together. You want to find clues.
wait, how does this work?
Things that are
Wait,
always
it's collapsing.
Flux is an interesting way to describe that.
All right, yeah, I mean, so things that are always in the same set. They never appear separate. Could collapse. This is potentially a collapse inside the package. And then you discover that two scopes are always together. So it doesn't even and I'm saying you can do that. And that might cut down on colors and have short radios.
I just had a question. You mentioned at some point, so when you have like a internal or recursive expression object, so like a syntax binding and a regular binding, like
well, yeah. So
Wait,
the
where is
complication.
the code for the macro? Okay, I might actually want to try to start hacking on that. I think never close the code and have no idea how it works. I could try.
So the complication is when you have a so you wouldn't necessarily
well, what I would need to do is put that in there and then think fine.
and all of this
So that is all the biggest
we'll have to explain this process. This is a frustrating but I can read this one.
Looking to get
So, Spencer.
You were first one to give me
Oh, we're just switching back.
Some people are hanging the microphone down here.
That's what they, yeah. Okay, that's okay.
Did he do the, is he related to Optimist?
No, no. I asked him if he was the one who was telling you about the spreadsheets talk. It's kind of thing. But what we were just talking about was formal methods. And I've never seen any software system that does formal methods to everyone's satisfaction. And he said, yeah, it's no problem. But anyway, I'm interested in all that, but the formal methods is the one that kind of jumps out at me.
Hello. Hello. Yo! So if everyone could please take their seats for our next session. So this next session is entitled Scripting, and I like to think of scripting as writing small programs that have high leverage. That is, programs that allow you to manipulate big systems and get big complicated things to do what you want with a small amount of effort. And of course that's something that Racket's great at, and that's the sort of thing that Byron is going to tell us about in more senses than one in this talk. So
that's just what we mean. In fact, the reason that we chose Racket, or I chose Racket for these applications, one of the reasons was Jay McCarthy's talk at last year's RacketCon, where he demonstrated just how much you can possibly do with as little code as possible. And that's exactly what we need to do in some of this. So I'll get on with it. I'm kind of new to the Racket community. It's Byron Davies, of course. I had the usual techie training, Caltech, MIT, Stanford, where I got a PhD for developing ontology and semiconductor manufacturing. Worked at Texas Instruments for helping bring the Lisp machine to reality. The TI Explorer, this machine to reality. Worked at Motorola, where we developed Lisp-based and web-based tools for manufacturing. It was very, very early on, about 1995, so it was pretty early on there. I've been working in a number of startups since. Let me tell you about the three things here. I'll talk a little bit, just a tiny bit about spreadsheets. I'm not going to show a slide though. When I offered to give a talk here, I offered Vincent 3 topics. One was the spreadsheet talk, well, actually these 3 topics. And at the time, the last 2 were kind of in their infancy, so Vince recommended to go with the first one because it was actually kind of concrete and easy to understand. But he agreed with me that at this point, we'd probably go ahead with more of the other 2. So to make the spreadsheet topic short, basically we created an object-oriented spreadsheet. We needed it for, actually I work at a school called Starshine Academy. We needed it for analyzing some school performance data, and it worked very well. And since I did that, it's now kind of disappeared into history. And it'd be interesting to think about integrating, because I know somebody did a GUI for spreadsheets and so on, but not to this session. The formal methods I'm going to talk a little bit more about. Oops, didn't like that. I'm part of a company called Ontopilot. You can find it at ontopilot.com. And basically, we're developing tools to analyze software. So static analysis of software. A lot of people are doing that. We have a couple of edges. One, we have a fellow who's been, one of our partners is a fellow who's been working in the area for about 20 years. who personally knew Dijkstra and Hoare and a lot of the other people in the field, had developed the things, actually built a successful company in 2000 or before 2000 for the Y2K problem, and did static analysis of software, made a lot of money, had a company of 600 people. So we have some background in this. So we were working on it and theorizing about it, but we finally decided to do a prototype. So we did the prototype in Racket, of course. Simple flow. You can't really see it from where you are. We start with the running program S. You find all the code that's or pardon. So you go out and find the program. So you got a problem S. Go out and find the program. You then expand it into all the software that's really relevant to that program. Actually do a conversion to disregarded commands, which then makes it very easy to transfer to logic, and then do some powerful analyses. And so our flow and complete flow adds a couple more steps where we do a weakest precondition analysis, do a logical analysis of the program, and then use that to find the faults. At some point you have to identify a point in the program and specify a post condition at that point. It's got to be true, so that fault wouldn't have occurred. And use that to track down to where that precondition was not was invalidated. We've also, as the red down here says, we actually did our prototype in Racket, and so we now have a system that takes a Racket program, gathers together all the Racket code that it needs, converts it to Racket syntax. Thank you for all the syntax developers. Converts it from syntax to Dijkstra-guarded commands, then to logic, and then we're a little fuzzy on the end things because we really haven't done them yet. But one of the important things about what we're doing, why we think we have a better chance than other people, is that Micron is just now coming out with a massively parallel finite state automata. On one chip, there's 256,000 automata, and that's going to be its assistance in helping to perform the logical operations, particularly simplification on large logical expressions. One of the things we use, you can't really see this, but what we did was, since it was kind of difficult to visualize all this stuff, instead of just doing print statements to debug, we actually ganged together 7 instances of the macro browser, syntax browser. And so you can visualize the entire flow through the system, and so that's stretched over a long screen. I really need one of those more than HD screens in order to play with this. And the details aren't important, but just expand out to deeper in programs, and intermediate language, which is syntax, and then into logic. So what I really want to talk to you about, what I want to get you really excited about, is our work on the X Prize. And this is a different organization. This is now back to Starshine Academy. It's this little school in Phoenix, Arizona, and we're competing for what's called the Global Learning X Prize. And so the new X Prize, the first X Prize was the one for getting man into space, or privately getting man into space. So a fellow named Peter Diamandis offered $10 million, the first company to get somebody in space and get it back. And sure enough, some companies tried, succeeded, and one of them collected the $10 million. Mind you, they spent over $100 million to do it, but it did have the effect of inspiring a new space race, a private space race. So there's been other X Prizes since. Next week, they're going to announce, I think, the winner for the tricorder X Prize for $30 million. So it's kind of an exciting deal. Last fall, they announced the Global Learning X Prize, which is an X Prize for developing best tablet-based software to help young kids learn reading, writing, and arithmetic. And the age is 7 to 10 years old. There's some other constraints on it, that the software has to be open source, and there's a little problem here. It also has to be run on Android tablet, so we'll have to work on that. Schedule details can't see, but basically there's 18 months design and build. There's going to be some space in the middle to evaluate. So they're going to identify 5 finalists, and then there's going to be 18 months of field testing where they'll actually try it out and see which one is the best solution. The awards are, each of the 5 finalists gets $1 million. The final winner gets $10 million, and apparently there's an extra $5 million for women owns teams, for women managed teams, and of which one is ours. So there's substantial money out here. The real goal is to eliminate illiteracy worldwide. And this is a technological step towards that. You can find out more about that at XPRIZE and the XPRIZE forum. So what are we doing in this? Well, we selected the Racket as the platform, based on just the success of Racket at real and imagined applications. But we know, and we're facing this as a charter school in Arizona, education is broken, and not just here in the United States, but globally. We don't want the XPRIZE to be exclusively about the 3 Rs. We think that we offer a holistic education. We think that the solution should have a component of that. We have a great team just by luck and persistence. We have a great team of systems thinkers, computer scientists, etc., working around us who are volunteering their time to work on it so far. We have our own laboratory, because we have a school, so we can go walk down the hall and just try things out. And we think that the solution ultimately will be as valuable for our students as for all the other students around the world. So how are we competing? We're taking a slightly different tack from a lot of the teams. There's 198 teams around the world that are competing for this. Because it's open source, the big companies have elected not to get involved with it. There's a lot of other people involved. So other people are taking kind of a software-oriented approach, that is just starting to develop stuff in hopes they'll eventually roll into a solution. We took a kind of different approach, said, all right, we need a theory of learning. We need to figure out what's the best way of learning this stuff, and then we'll figure out how to get it on the computer. The theory of learning, you have to figure out what the content is going to be. You need to design the experience and design the overall system, because this isn't just one kid with a tablet. There are a bunch of other people around him that may either help or hinder them. And then, of course, there's the programming, which we need to get to. So in the theory of learning, we investigated black swans of learning. And by black swan, I mean examples of learning that are so productive and powerful that they strain credulity. You almost can't believe it. And the first example that I knew about was a language teacher, a fellow named Michelle Thomas, who could one-on-one teach somebody a new language in 3 days. Now that's obviously can't be the whole language, limited on nouns, but he taught basically the verb structure, pronoun structure, and a few nouns in 3 days, 20 verbs, 20 tenses on hundreds of verbs, and did it across multiple different languages. So I thought, well, reading can't be much different from learning a new language. Let's look for solutions like that for reading. And we actually found one. And we're working with a fellow who's got a method for teaching reading. But beyond it, teach how to read English in 12 hours. And English is one of the most difficult languages in the world to read. So we found solutions in math and reading, and also in another area. And the central theme is this notion of guided discovery. It turns out that just teaching stuff, lecturing doesn't work, but neither does just letting the kid go and try to figure out the world by themselves. They need to see a guided component to it. So we're working on that. We developed relationships with key collaborators bi-coastally in this country and in Canada as well. And we've begun testing the pre-technology solutions at our school. So why Racket? Why use anything but the second best programming language? It's powerful, cohesive, solid, reliable, interactive, graphical. It's parenthesized. I have 40 plus years of programming Lisp, and so I kind of favor the parentheses. And then there's an excellent execution environment, and the summary for that is batteries included. One of the cool things that we came across was PICs. Now here's the thing. This is a graphical object, and you can size it, scan it, and you can put multiple objects into it, make one pic out of it, and so on. And so that was an interesting concept. So all languages must have, all graphical languages must have something like that. But what was cool was that they're in the REPL, so you can do some evaluation and play around and it generates a fix. You see it right there. It's like, wow, that's really cool. And another thing that we're just beginning to look at, this just occurred to me in the last week, thinking about this conference, is that part of our job is to be in the publishing business. That we're going to have to create and display content for kids in very flexible ways, which I'll show you in a minute. And so we may need something like Polyp, which is available basically as part of Racket, to do that for us. Another thing about why Racket. So working on the reading application, and I'm working with this brilliant reading theorist on the West Coast, and working with her for a couple of months, and really developing software. You import the CMU pronouncing dictionary, and lots of interesting things. Created an app to display the sounds on the screen, so you click on them and hear what the sound is supposed to be, things like that. But there was something a little bit wrong with her solution, and I don't mean to cause her problems, but she created this phonetic alphabet that was basically numbered 1 to 39. So it was hard to remember which sound was which. And I was thinking, well, after a couple months, I couldn't remember which was which, so how are kids going to remember it? So I might as well look for a phonetic alphabet or a graphical alphabet. And it turned out there was a guy in Philadelphia who had a graphical alphabet for reading. And so actually, over the course of the weekend, I had all this infrastructure already built, and I learned about kits and how they work and so on. And so I sent this to the fellow in Philadelphia. And thought, oh, gee, this is exciting! Accomplishment just over the weekend. And what it says is, sentence to phonetics. This is more fun than sex. And so feather is the symbol, is the symbol of feather. Igloo is the is symbol, and for is the more symbol, because that's the end of more. And umbrella is the symbol, and you figure it out. And so we got that far. But it turns out that's only the first step in his reading. The first step in his reading is to get kids to read the phonetic alphabet. And that doesn't take long. It takes a few hours. And then the next step is to develop a scriptable form of the phonetic alphabet so that you can actually write it by hand if you wanted to. And he was doing this with tutors so that he would use it to annotate text with the phonetic characters. So the igloo is just a curved concave downward, and the for stays the same. The umbrella turns into something much simpler. The man turns into something, and so on. So it has this phonetic alphabet. Well, the invention here was, well, it's all great. You have phonetic alphabets. How do you learn English? Well, he took something from, how much time do we have? 3 more minutes? Almost done. He took something from the Muslims and the Arab Muslims had developed a little over 1,000 years ago, and that was diacritics. The Arabic alphabet doesn't have vowels. It's very hard for kids to learn the Quran. And so they discovered putting diacritics in the lines above the text for the vowels. And other people inherited that after that, but it didn't appear in English until about 5 years ago. And so the next step on this is to present the English and then provide the diacritics as training wheels for the kids to see what the sounds are. And this isn't important probably for any of those, but if you have a syllable like O-U-G-H, there's lots of possible pronunciations for that. Kids can really stumble on that. And then there's another step. I thought, well, there's a geographical alphabet. So he actually recycled the consonants and said, well, kids can learn consonants. But in my classroom experimentation, I found the kids, it's a whole other page. They need to learn the consonants and develop an alphabet for that too. So there's a bunch of projects, and there are more than this that we're interested in getting done in Racket. Porting Racket to Android, implementing these learning systems in 3 areas: math, early reading, and systems thinking. Developing architecture to manage the whole system. Math exercise generator to generate, and there's this fellow who did the math solution has thousands of exercises out there. We ought to be able to compress that down so we can have a generator. And then finally publishing this text rather than using in a beautiful way rather than some of the other ways that I showed there. So that's what we're doing. We're excited about it. I just, like an hour ago, I got a call from a CEO that she's been out looking for money to fund this. She called an hour ago, says she's through the XPRIZE organization, she's hooked up with an investor in Hong Kong and they put money into this. But even if we don't have money, we're certainly open to gain sharing. That if we win the moolah, then we'll share it with developers. So if anybody's interested in doing some exciting application-oriented projects, we've got them, and there might even be money in it. Thank you.
So we have time for a couple questions while Samuel, the next speaker, sets up.
Yes.
Your plan looks very straight line. It doesn't accommodate for loops.
Well, we got plenty of loops.
What I mean by that is, I didn't notice formative evaluation in the plan. I didn't notice goal setting or diagnosis stage where you actually diagnose why people are illiterate and how that might help the solution. The formative evaluation would be helpful if you set up a goal, immediate goals that you're going to achieve at some point, so that if you don't reach those goals, you can move back and figure out what in the process went wrong. I would have a formative evaluation before being delivered, so that you have a preliminary idea of how it was in population that you did not take into account. I'm absolutely convinced that the sunshine, star kids, school, Starshine community school, everything is homogeneous in one regard, and you definitely want to do a homogeneous solution, if this is supposed to be a worldwide problem. You can go across the border to the dollars at least and figure out.
Well, actually, I'm actually doing this in kindergarten class, trying it out actually on kids lower than age.
Well, but I'm opposed to go across the border.
But yeah, we are across the border. Out of, we started with a K1 class of 30 kids. There were 8 Somalis whose home language was Arabic, and 6 Hispanics whose home language was Spanish.
So it's really just a suggestion of.
But it's homogeneous. They're little human beings. Yes.
I'm just going to make a few more things that I see you listening from your world. Otherwise, all the rest.
Appreciate it. Thank you.
Okay, so our next speaker. Well, first let's thank Byron again for that. Okay, so our next speaker is working on scripting a very different kind of system, but one that has a complex control interface and thus will be illuminated by being programmed in the second best programming language. So Samuel Belsky will talk about scripting begin with Racket.
Good afternoon, everyone, and am I too loud? No. To continue the previous session's theme, my name is Sam. One of my advisees is a graduate student getting a PhD at Indiana in 1 week. Yeah, it's for her, not for me. And I'm here to talk to you about scripting GIMP. GIMP is a new image manipulation program. I think most of you knew that. I'm using Racket. And I'm from Grinnell College, a small liberal arts college in the middle of more or less nowhere. And so the context is about a decade ago, our department was rethinking our intro course. The obvious part was that we were going to use Scheme for our intro course. The stupid decision was we just didn't adopt how to design programs, but that's okay. We looked at other directions. And we had 3 main inspirations. First was Mark Gusdile was showing a lot of success at getting particularly women to stay in CS by doing image computation and other things. Students also seem to be very excited and continue doing their computer science homework even after they've met the requirements. Looking further back, Mike Eisenberg has this wonderful thesis at MIT on Scheme Paint, where he looked at what it means to script applications, and that is a motivational tool for people who might not otherwise want to program. And then my colleagues Henry Walker and John Stone have been doing workshop style CS for 15 years before, 10 years ago. And so we wanted very much a workshop style, wherein most of class time is students exploring, not listening to someone like me in front of them, because you don't really learn listening to people in front of them, or maybe the other people you don't listen to. And so we thought about the fact that, nice computer, GIMP comes with Scheme. There's a nice little Scheme console here, and maybe you can even see it. Maybe not. And it's real Scheme. You can type complex expressions like 2 plus 3 and get 5. But you can also control GIMP. So we can draw as normal. We can set the color. And learn to type in front of an audience. So I'll do a shade of red, more or less. And you can see now I'm drawing in red, and I can, this isn't very exciting, as you can do in lots of things, but of course it's GIMP, so you can choose really interesting brushes. And draw with lines as opposed to colors. And so it's a little bit more powerful in many ways we think about drawing. And we have this amazing ID, which is resizable, sometimes. Oh, look, you can make it larger. And if you type incorrect Scheme, it gives you really helpful error messages like and you can enter fractions. Well, okay, maybe you can't enter fractions. So it didn't really seem appropriate for our introductory students. Now, at the time, we'd already been using this wonderful, great Scheme environment called Dr. Scheme. And so we looked at how we could take Dr. Scheme and make it work with GIMP. Nice. Is the text legible at the back? Okay. So here's a simple program that takes an arbitrary image. This one is also resizable. And draws an X on it. So it starts at 0, 0 as the top left corner and goes to the width across and the height down. So that's that diagonal. And then it also draws one from the width across and go down. Also, I can say, for example, run and do this wonderful thing on image 1. And you can see we now have an X drawn in lines. Maybe we should see a different brush. GIMP does not necessarily have the best brush names. And there you go, you can see the actual color. So we have some potential for doing some simple things. But the other thing we noticed about using, actually, let's see. And it means you can start doing things as you think about them programmatically that aren't necessarily possible just directly in GIMP. Like someone could have done that by hand. But you can't like rapidly change the color while drawing. So we can write a loop. I apologize for my Scheme style or my Racket style, but you can write a nice little loop that every 10th of a second changes the color. It's running, and so you can see as I draw, the color gradually changes. And so this shows students that with very little Scheme, okay, they just have to understand recursion or some kind of looping structure, you can build new tools that weren't there before. But there's a little problem here. Other than that old console being just a console, this doesn't feel very functional to me. Does it feel functional to you? No. And why do we love Scheme? We love Scheme because it's functional. So one of the things we started to do is look at ways we can provide them with more of a functional model of images within the GIMP. So the simplest one is thinking of an image as a function from positions to colors. So we have our nice little lambda expression that takes the x coordinate from the y coordinate and gives you back a color. In this case, The red component is the x coordinate, the y component, the blue component is the y coordinate, and the green is some function over 2. And if all goes well, we see a nice little horizontal blend there, and you can see if we change the functions we use,
Very easy.
we can make the whole thing crash.
Let's see.
Never do a doggy condition. Let's see. Do I want to? Sure. Oh, that was fun. How many people have been in this situation before? Oh, good. I feel a little bit better. This is not Dr. Racket's fault. You'll notice that at the top it says unsafe. That's because it's my So let's see. Where's the image compute? From there, we start looking at transforming existing images. So we have a picture of a kitten that we use a lot that we found a few years ago, and it's in the public domain. And so we can have them do variants on it. That's probably the best. Let me do a similar one first. Before, there we go. Okay, so here's our kitten. Here's our kitten. There we go. Isn't it nice? A good feeling. Don't you want to see some random badly garbled text on it to be funny? And we can say, well, I want a variant of that image. And here's the function we're going to use on each color. And I'm just going to complement each color. And we want to show that image. You know, they represent it as an integer, and you see a functional model of transformation. It's pretty clear to our students. From there, we can start talking to them about more higher order programming issues. So for example, they learn that there's an IRGB subtract function that takes 2 colors and subtracts one from another component by component. And so we can say, well, image variant is supposed to take 2 parameters, an image and a single parameter function. How do you make a single parameter function from a 2 parameter function? It's time to learn cut. And so we can remove all the red from an image with that nice little expression. There we go, and it actually worked. And there's our kitten with no red. And what else do you think about when you're doing these transformations? Well, you may want to do more than one transformation. And so if you want to do more than one transformation, you probably need composition. And composition is a little weird because the order of operations matters a whole lot. So we can either subtract all the red and then complement, or complement and then subtract all the red. Is there a scheme convention for compose? I was discussing this with my colleagues. Anyone use a particular symbol for composition?
There's the word compose.
Okay. We use a little O because it looks more like math, but maybe we should have used compose. And you can quickly see that they start to learn, think about functional operations visually. So here we've complemented and then, there we've complemented and then subtracted all the red. Here we've subtracted all the red and then complemented. So this is sort of pure functional. But sometimes we want to do a combination of things that feel GIMP-like and things that feel functional. So there's a selection tool in GIMP, like there is in almost every graphics program. So we could programmatically select something and then transform just the selection. I use complement because it's really easy to see. So below kitten, and we complement. So there are immense power to, you know about the power scripting. The students quickly see there's an immense power to scripting. And then here's something that's probably going to make you feel uncomfortable. every color is represented as an integer, which means that the way we transform each color doesn't have to be a color function. It could be multiplied by 2. And so we can look at our kitten with each color multiplied by 2. And it makes no graphical sense, but you can get some fairly interesting effects. And I'll hope this one doesn't crash the computer like it normally does. And I can never predict these, but this is what happens if you multiply every color by 1.4. At least it seems to be what happens if you multiply it by. So the students have a lot of fun playing with the different effects they can get in abnormal ways. Now this breaks typing, so I don't think we can ever use type bracket for this, because I'm treating colors as numbers, but it helps the students understand that there is an underlying representation that they have to make about. So that's it for the pretty pictures for now. Let me talk a little bit about what we've seen. So we knew from the Gazile work and from the Eisenberg work that students are motivated by making and manipulating images. And it's really fun for me when I walk up to their computers and their desktop is something they did in my class. I showed you higher order programming. We did that in week 2. So they learn cut and compose in week 2. That's not a normal intro CS class. They learn cut and compose before they learn how to write their own procedures with Lambda. The thing we didn't expect is that the students say, like, when my code doesn't work, I look at the picture, and the picture helps me figure out what's wrong. And that's such a great experience, right? It's like seeing 5 when I expected 2 doesn't tell me a lot. Seeing like in black over here when I expected white actually seems to tell them something. And we also find that as people who like to teach math, this model really does help them think mathematically, because you can't really do graphics without some math. Behind the scenes, what are we doing? Well, we needed a way to hook up 2 programs. We're Linux people. I had one of my students look into it. He said, dbus, use dbus. So we use dbus for this, which means we had to extend GIMP, which at the time didn't support dbus, to support dbus. The internal GIMP scripting engine didn't really believe anyone would want to deal with pixel level data in large chunks. That's what they call tiles. So we had to build a tile iterator as a plugin for GIMP. The scripting language assumed we use triplets for the colors. That tends to use a lot of memory and make the garbage collector start a lot, so we tend to use an integer representation that you saw. Then we needed to make Racket communicate on dbus, and it was probably late at night, so this wonderfully funny title, Racket on the dbus. No, okay, it's not wonderfully funny. And then the other thing we found about GIMP scripting is that it's not easy. Students have to think about layers and weird commands. So we spent a lot of time building a Racket wrapper around most of the complicated built-in things, and then we also had to do some parts in C. So it was really fun writing the image variant thing that has to take the GIMP model and take in the beautiful lambda that I get and somehow apply it to each pixel. That was great. It really was. There are lots of problems. One is an obvious one that someone was going to ask, which is Racket's already great graphically. We just talked about on the previous talk. Why bother with something new? But we really do feel that application scripting is a powerful model for students. They learn that they can build something not just for themselves, but that someone else can use. Like once you have that, make the brush change the color and it actually does something interesting, or once you have a new filter, you can share that with someone else. That's a powerful feeling. And that's different than, look, I built an application that you have to run from the command line. This is like, you can plug it into GIMP and you're fine. dbus is Linux mostly. I think there's a Windows implementation. I think there's a Mac implementation. They're kind of funky. So this only works on Linux right now. GIMP is not always expecting us to do what we do with it. So occasionally a student will make something happen, and they'll look at the screen and nothing has happened. And we know that it's happened because we can query the image, and that's a difficult thing. The GIMP designers didn't say, oh yeah, you should be able to programmatically choose which brush you use, and which brush doesn't matter. Do we use a paintbrush or an airbrush? And then I coded this before I thought enough about Racket, so it's really ugly scheme as opposed to really beautiful Racket. So if you ever look at my code, you will discover that. And I am right at the time that Sam wants to say it's time for 2 questions. One.
Well, first, let's thank Samuel.
questions, and also for the next speaker to start setting up.
I inspired no questions.
Oh, there's one in the back and one on the side.
So you said that Racket has a couple of ways of producing images already, and that's signature. Could you turn your interface into GIMP into a way of programmatically building things without having to have GIMP, active and running and on the screen, and use GIMP as a library for Racket, so the vertical relationship?
Given sufficient time, yes, probably. GIMP will run headless. I have not tried to do so. Time is an amazingly limited part of life. I guess that's probably something that should go on the list of things to do. And so
I sent you an email about a page I saw yesterday at Strange Loop about a Cambridge project. It's art. Just check your email. Thank you, Dennis. Truly, that's good advice for all of us.
So let's thank Samuel again. Okay. For anyone who saw Matthias's excellent talk at Strange Loop yesterday, they know about the importance of Big Bang and universe. And today, Vishesh is going to talk to us about taking that power and making it easier to share it and use it for anyone out on the World Wide Web.
Thank you, Sam. So I'll be talking about Big Bang. So my friend read a great book called Realm of Racket, and he was all excited to share the game he made with his friend. So he pings him and says, hey, I created this great game, would you like to play it? And he was like, sure, why not? And he meticulously sent him all the details, like download Racket, download the source. And he was like, okay, I'll download it later. And that's usually what happens, right? No one wants to download stuff. But they do click links, right? People click links all the time. So that's how Wellwin was born. Right, so the idea is you could post your Racket game in this website and click compile, and it will compile it behind that, and you could just play the whole game within the browser. So we are taking this idea from Scratch, which has been there for a while, but we sure don't use the toy language, we use Racket, right? One of the other goals is to find weird song bugs and continue improving it. And along the way, we also created a Dr. Racket plugin so that you could easily publish your games to web browser. So let's try this. The link is bigbang.ccs into the video. So, yeah. So Steve, me, and Ben uploaded some games from Racket 2. I'll just search for them. So this is my favorite one, and it's archery. Here you go. So, okay. Okay, yeah. So, yeah. You can see the ring spade. I'm going to try to hit the center. And once I do, I'll switch to the next game. Okay, last try. Oh, great. This is reasonable. Switch to the next one. And now let's try Planboard. I guess everyone knows what that game is. Okay. There you go. It's still easier than my touch phone. See? Yeah. Okay. So now I'm an expert, so I'm gonna poke it and make it harder. Yeah. I'm gonna have hard work. I'm not a robot. Submit. Yes, it's gonna take a while. I don't have non-machine time. So. Turns out and slower. Anyway, yeah. My intention was to make it other way around, make it faster. Yeah, sorry about this. Okay, so oh yeah, I should probably show. So here's the Wilson plugin. This is Game Tetris from Software Practical. I would just write the code here and do a song run, and it will take a while. Anyway, so it's taking a while, so I just, it will show up here at some point. Oh yeah, I did. Okay. So this is Tetris. Okay. Yeah. So the site architecture is pretty general. We accept that we use Racket web server. Otherwise, Wavesong for Racket to JavaScript compilation, MySQL, Elasticsearch for full text search, and I use Nginx as reverse proxy. So Wavesong is, like I said, a Racket to JavaScript compiler. It was created by Danny Yu and currently maintained by Jane Excel, and Emmanuel and Darren contributed a lot that made all this possible. I just did stuff. So hashtag Wavesong is a subset of Racket. It doesn't support the full Racket. And so some changes to your code will be required. And typically, if you are making a game from HTTP or NF Racket, these three four lines should just work. And yeah. Wavesong has some limitation. One of them, the biggest one, is like you can't directly install Wavesong from Dr. Racket package manager. It doesn't support full Racket, so if you are using fancy features like classes, keyword arguments, probably macros, but macros is about, yeah, and image literals in your Racket, so which is very common in HTTP books, that won't work. So yeah, we are working on that. Also, Wavesong lives on top of a very heavy runtime environment, so even if your game works very well on Racket, it may perform very badly on Wavesong. So now I have time for more time. I will speak on experience writing this web app using Racket. There certainly has been some good things and bad things about it. So coming to the good parts, I really like expressions because it's of the purpose of template, right? The purpose of template is to insert arbitrary code inside your HTML, and that's exactly what expression did, except that I didn't have to learn a new language, and I wasn't limited by the templating language. Of course, your designers won't like it, but I'm a programmer, so I'm okay with that. One selling point of Racket is continuation, which can be useful, not very meant for me. I'll speak about it later. I particularly like parameters. It was an awesome way to manage global state. I use it to manage sessions, and I clearly see how I could extend to more complicated applications. And because of the parameters and other cool language features like macros and the current state of web server, I think we probably don't need a full blown big framework. We could, particularly for the small projects like this, I could just create a small framework as per my taste as I build something. So yeah, that's pretty good. Coming to the bad parts, one of the biggest bottleneck was like lack of libraries. Typically, I expected this to be over in a weekend or something, but yeah, there was some families that weren't there, and there was a lot of grunt work I had to do. Particularly, I guess, an ORM because I really don't like writing SQL, plain SQL. It's this code and string, and every time you have to change, you feel like you have to pull your hair out because yeah, you have to change information and stuff. Yeah. So rather than complaining, I started working on some PSL to make which would compile language SQL is a work in progress. I also built an Elasticsearch library. So yeah. So I think yeah, clearly Racket needs more library for that. Coming to continuation, I used it for registration and login forms, and it was useful there. But I don't see how it would be useful for other like UIs, like shopping carts, and it was pretty useful. And I wanted me to do some grunt work because everything was available on Linux provider. So I was probably more confident about my correctness. But web applications these days are built using RESTful architecture that is within the same request to provide all the information, and most of the application, the single web application do that, right? So I don't see how you could build continuation in that. And one of the biggest drawback was like you can't scale continuation out of the box because the state is local, right? If I'm using continuation, I just can't go on more machines, start the web server, and put the engineers on front end and scale, expect it to scale. I'll have to make some distributed continuation manager first, and that's clearly that I can't do in any case. So yeah, we need some distributed continuation manager that will store the state and some distributed store. So that's all I have to say for now. I'd like to thank Steven, whose ideas hosting was, and invite you all to go to webbank.ccs and your preview and upload your games, play there, and thank you.
Okay, so I hope everyone can take a break from playing all of Shesh's games on their laptop to ask a few questions.
Is Whale Song Pac-Man complete?
No. You mean can I write Pac-Man games?
Have you written Pac-Man?
Oh no, I haven't. But I think you should be able to write Pac-Man. Yeah.
Last time I said that he hadn't actually written Pac-Man, they did this.
Whoa. Any other questions? Okay, well, let's thank Vishesh again. So I'm happy to announce two things. One is that we have a break coming up, and the second is that we now have some full-strength high-test coffee to accompany that break. So for the next session, we'll resume in half an hour.
Oh, yeah. Has that made it?
Everything seemed to go well.
Okay, great.
The whole thing is in one video.
That's fine.
Okay, because like they were so quick. I'm like, it seems like it's easier to chop videos up than it is to magically synthesize the person.
It's not any harder for us to.
So, I also. First talk, I was very zoomed out because he was very moving. Well, little. The other two, I zoomed in.
Inconsistent zoom a little bit. Okay, that sounds good. It looked like you were doing fine when I last back. So.
Okay, well, hopefully I didn't mess up too badly.
Don't worry, my whole talk slap. There won't be any moving.
Yeah, so we're not actually going to run the camera for your talk, Spencer.
Oh, thank God. Okay.
I was going to say one thing is if you point at the slides, then don't
face away from the camera.
Yeah. Oh yeah. Oh my God. Rishesh is the whole camera angle for Rishesh.
Yes,
Like,
even if you are reading off your slides, don't make it look like you're reading off your slides.
I mean, I'm not saying he was reading off the slides. He was pointing, right?
I mean, sometimes people are reading off their slides, and sometimes people are
just. I wasn't blaming any particular person. I'm just saying that that's something that note about.
Right. Right. No, I mean, I like it, but it's accurate.
I guess I don't know. He told me my work.
Okay, have you been downloading that images off the camera?
I've only downloaded the ones that game. No, I didn't.
Okay, but it all
goes through.
From your
Oh my God. Oh, I think have you seen joining us? The last few times today, you're going to be online. So you will. Oh, yeah, we did this one. That's why we have all the cameras and all that. So online, we're streaming it live. They're going to be on YouTube. Hopefully, in a few weeks. It's just a lot of time it takes to actually copy paste everything together, but they will be there. Thank you very much. Pretty pleased. See you next year.
Yes, I haven't done my investment today.
Yes.
They want to do that. I use Go ahead. You have
I also want to grab a seat so that I can charge my laptop. Which some my laptop ran out of power. And covers worse than most things. So, well, it is maybe next. Just gonna stand up there and hear. Wait, sure. I haven't stopped it on this one. Yeah, I just went through just saying that. Oh, that is not even close to oh my God, this is smaller than my usual. What? How is this potentially like these two options? Neither of them was the one that was on. That's a good one, right? Hey Tony. Yeah. Hold on, 2 more windows. Is this readable? No, I'm talking.
Well, I don't know. I
Yes.
don't know if I'm
Alright,
I think this has started with the conversation with Sam about other web server not doing streaming. Next one, yeah, but like, I kind of want to.
Thank you. Great job. I'm taking off.
All right. Well, thanks
Just
for coming.
goodbye. You did a fantastic work.
Why is clicking on one?
Of course, and also,
Well, so it works and I actually very recently some pretty
That's usually lost.
All right.
Do you need to wear black and white for your terminal?
Black on white.
Yes.
White is not available.
Yeah, this kind of causes problems.
Oh yeah. It's big enough.
Well, let me check this from the back.
I think that's gonna be good.
It looks pretty large.
That's just not. Yeah, I'm gonna make this. I have. Yeah, I know, it's fine. All right, good to go.
Oh, okay. You can move a bit. Just one thing.
I'm gonna be on at like Google typing, so it's gonna be hard to.
Oh, okay, okay. Just don't move past the edge of the screen, basically. That's the main thing.
You don't need all this.
Yeah. Not a believer. Why is that information? Who added that? That was him. Of course it was.
Oh, yeah.
Yes. Well, actually, anything goes.
No. That is obviously true. Oh, yeah, bootstrap is not really it. Bootstrap is as soon as you bootstrap, oh yeah, I was just gonna rearrange the water part of this. I was gonna work out all the CSS.
All right, well, nice to meet you again. Yep.
I mean, I remember now.
All right, thank you for those references. I'm looking forward to it. Okay. Do you? Okay. Okay. I mean, I will browse through it because I need to refresh my memory anyway. All right. Thanks. See you later.
So, and I always wanted to have a custom database. So, basically, that's an intention. It's not nearly That's okay. Rest.
Full stack JavaScript. I want to use JavaScript.
Hey, so we can ask for the pro. Yeah. Basically just run Hey guys, I didn't like the cover. It's terrible. Please, the cover is long. Alright, no, and you select all of it. Yes. Oh, boy. No, trade margins.
What is this going on?
Just he has the entire course of the entire
It's like sleep going best. Rising up package. Oh, I should I think it's okay. You'll like Robin bookmark in life on whole emergency key. So yeah.
That's a good bookmark to have. Is it like randomized or no? It's just that would be an amazing.
I have considered writing a Chrome plugin for this, so I can just like keep throwing in different like.
There's nothing online. There's stuff online. There's nothing. Well, the fact that I have a link to the Magic Gathering search engine.
Facebook, Twitter, Hackers, Google Play, Netflix, YouTube, yes, the search thing.
Yeah.
Just bringing it up right now. Okay, well, I got everything. Right.
I'm not, well, looking back, I think what they meant was that, yeah, it's having yeah, maybe it's just the UI. Like, with the UI, maybe that objects. Yeah, it works. Yeah, like basically uptight objects. Yeah. Something. You could say that Unix file system.
Yeah, like a string type.
Yeah. Like a little bit of that. What's that? Fuse? Oh, there is that. I also believe that, like, I mean, ultimately you have a structured and then you can use code that operates on an interface. I'll get to it in a minute. So it's an interaction through an interface. I think it's
Yeah. So you can think of plan just
taking it further. Yeah, too bad about that.
Like so you don't use it. I think it's a bit nice.
Yeah. Right. I'm teaching a personal boot camp. It's like extra double because we're fitting water like three. I'm doing it with Bert. We'll see how it I'm letting them use whatever they like, provided that they check ahead of time and they can make sure that they're using the right terms. Like as long as they can do everything in terms of stuff and fix size and I can read the code, they can use whatever they like. I was doing examples of the Canvas class on the theory that systems and I think perhaps, but I think mostly I'm not going to totally drop lots and everybody.
Yeah.
Are you excited?
There's one slide. Remember what I do?
I'll hand it off to you.
Thanks for reminding me. I can probably figure it out.
Yes, so, all right. Are we ready to rack it? Now, it's getting to the end of the day, a long day, and if you've been at Strange Loop this week, quick show of hands, how many of you were at Strange Loop? That's most of us. Well, for those of you who couldn't make it, keep an eye out next year because it is an awesome time. And so for those of us who were there, it's the end of the long day at the end of a long week. But it's time to pay attention here because by now you're surely inspired to go create some great things using Racket, using lots of great applications. And how are we going to create those applications without libraries and tools with which to do so? And so that is our session now, and we've got some great things for you to pay attention to because it will surely help you build applications of your own. But before we do that, we have a quick public service announcement from Tony Garnock-Jones, who wants to show you something about the Racket server.
Hi, I have been experimenting with making a new, just a new user interface for registering packages and for searching for them. And it uses almost all of the existing code except for the very front part, which is the user-facing web pages. And you can get to it on beta.pkgs.racketland.org, and I'll put that up in just a second. And it's really just a different front end. What I'm looking for is feedback on the design and any design ideas that people might have. And if people could try it out and tell me about any bugs or any problems or anything they would like to change or fix, that would be ideal. Please just try it out and let me know how it goes. Now, an important thing to note about this is that it is not connected to the main package server. So if you do Racket package install and you're expecting to see something you entered into this website, it's not going to show up. Instead, you have to add it as a different package catalog to your catalog registry. But come and talk to me about that if that's something you'd like to try out. And those are my contact details, and that's the URL. So please give it a go and give me some feedback. Thanks.
All right, thank you, Tony. So our first speaker here today in this session is Jack Firth. And Jack claims to do absolutely nothing interesting during his day job, but he loves learning. He took 4 years to learn that he didn't really want to be a mechanical engineer. He actually wanted to write software, and more specifically, he wants to write software in Racket. So Jack is going to be talking to us about macro expanders in Racket, say that 3 times fast, at the end of a long day, and specifically about extensible macro expanders. So take it away, Jack.
Is this thing actually working? Nope, not at all. Okay, awesome. Hello. There we go. Okay, so my talk is on 2 libraries I made. First one is generic syntax expanders. And I'm going to open with a very controversial statement. Macros are really great. And the alternate title for this talk is how I spent way too much time stumbling around how the syntax system works and getting extremely confused. So macros are really nice. Pattern matching is also really nice. In Racket, pattern matching is implemented as a library with macros. There's a whole bunch of Nice, cool analysis, figures out when you do branches that interleave and makes sure that you only check things once, and does all the binding and expansion you need. Now, most macros have a closed grammar. When you make it, you say, these are the things you're allowed to do, this is how the syntax is, that's it, that's the end all be all. When match has an open grammar, you can add new terms to match and new ways to define certain patterns in match. So, for instance, if I have a function that says this is true for lowercase letters, I can make a match expander that will only match lowercase letters from that. Now, it just uses a little bit of sugar, it's just a little sugar around the built-in conditional matching. Now, once I've made this match expander, you can match a list and use this lowercase letter pattern in your match patterns, which is really nice. Complex macros like match often have DSLs embedded in them, domain-specific languages, and often it is wanted that you provide a way for users of your library to extend this macro with your own arbitrary submacros. Match and syntax parse both do this. Match with match expanders, syntax parse with pattern expanders. Yeah, there's also that in require and provide. So generic syntax expanders let you create an expander type. And with that expander type, you can specify how macros use expanders that you've created in that. So you can add extensible macros like match expanders or pattern expanders onto existing macros that don't have extensibility without having to change the underlying implementation. So if I have some static closed macro foo base, all it does is you have to give it strings, and it just prints them all out on the line, each on its own line. Nothing too special. I can make an expander type called foo, and I can now make a new version of the foo macro, where all it does is it first gathers up everything you've given it, expands all of the foo expanders, and that expand foo expanders gets defined when you make a new expander type. And then the expanded forms get passed down to the base foo macro. Now, you can use it exactly the same way as the base one, but you can also make your own foo expander. So in this case, this is a little macro that will take some identifier unit and just turn it into a string. And this is so unhygienic, it might make pure schemists want to throw up. But the cool part here is we can now add our own little special foo macros into the grammar of foo without having to change it, or without having to change the implementation of the foo base macro. So for something a little less trivial, how many people have used the Racket command line parsing library? How many people found it to be kind of brittle and you kind of have to do some weird stuff to get things dynamic? And yeah, okay. So command line flag grammars often have a lot of really common patterns that you repeat over and over, and it's really hard to abstract over those patterns. Now, some of these are flags that just toggle a parameter and set it to a certain value, or flags that just, when you have them, they toggle parameter to true or false or something. Now, it would be really nice if we had easy ways to pull out those patterns into their own little macros in command line, and we can have some nice special syntax for those specific cases. Well, command line ext is the second library I wrote, and it uses generic syntax expanders to add a layer over the base command line grammar, where it allows you to add your own expanded types. So you can just sort of make your own little command line flag expanders. And for an example, suppose we have 3 just Boolean parameters that you want to toggle with flags. So the standard way to do that, just make a parameter for each one. They all default to false. And with command line ext, there is a toggle params command line expander, where I give it a bunch of pairs of parameter, the flags, the description, and it will turn that at compile time and transform it into the form that the Racket command line expects to give you the ability to pass in these parameters, and it will automatically toggle those parameters when you pass in those flags. So you can call it like this, and it does all of the same things that the base Racket command line library does, where the single switches group, and you get the n dash dash switch to let you do all the crazy stuff. And all of this will let you toggle those base parameters, and you don't have to write any of that mushy imperative code that sets parameters when you're parsing your command line stuff. So, another example, suppose we have a compiler, and one of the parameters that you can tweak when you're running it is the optimization level. Say it defaults to 1, and that does no optimizations at all. Now, there is a natural num param command line flag expander. And what you do is give it a parameter, a flag, and then a list of descriptions. And for each one, it will add the number 2, 3, or 4, or what have you, to the end of the flags and make shorthands for setting that parameter to that integer. So with this, it expands to a form of Racket command line that understands these. So you can pass in, you can make ways to pass in various command line flags for specific optimization levels fairly easily. And again, you don't have to touch the parameter yourself. And this one is built on top of some underlying parameter, more general machinery that both toggle param and the natural number param use together. So if we want to make our own command line flag expander, for instance, suppose we want one, like suppose we're running a whole ton of compilers for God knows what reason, and we keep on wanting to pass in optimization levels. So let's make a flag expander specifically for dealing with optimization levels. It's just a little sugar around the natural number param, the flag expander, that just assumes you're using a current optimization level parameter, and it has a standardized flag name. So now, that old program here for trying to set the various optimization levels and specify what they are gets turned into just this. Just write optimization levels and then list out what their names are. It'll take care of toggling the parameter, doing all the setting, doing all the expansion, making it into something that the base Racket command line grammar understands. All of that happens for you at compile time. So, generic syntax expanders let you separate a domain-specific language's extension from a domain-specific language's creation. You can do these now in 2 different phases. You make a base macro that has your base syntax and implements the base forms, and then you can define a macro on top of it that will process expansions and figure out how to turn your expanders into the base macro form. This means that you can implement things like match expanders on top of a match that has no expansion. That doesn't need to be something built in to the match grammar. Same thing applies for syntax parser, and you can add these things in like a handful of lines. It's very easy. So this sounds all well and good. There are some problems. First off, I mentioned stumbling around the syntax system. I was serious. It is an extremely complicated and very brittle implementation that is extraordinarily gross. It works, but it's gross. And it doesn't respect syntax protect. And if you don't know what that is, thank your lucky stars, because it means you've never had to deal with die packs and that monstrous section in the reference manual about how syntax arming and taints and rearming and all that crazy stuff works, let alone wonder why it was needed in the first place. Now, what happens is the way generic syntax expanders work is they'll store the macro at compile time in something really like a gross opaque box, and when it walks the syntax tree, it will actually pluck out the thing in the box when you call the expand all expanders function, and it does all this in an extremely gross way that picks apart your syntax, which means that it examines everything, and syntax protect will blow up whenever you try and examine a piece of syntax that's constructed. Syntax rules automatically wraps the syntax transformation returns in syntax protect. So you cannot use a syntax rules macro with generic syntax expanders. There are much better ways around this. This is the way match expanders are actually implemented. They do things with a structure type property. And I ran into some issues with that as I was stumbling around the syntax system and ended up going with this more trade-off approach. Context you need to. You cannot, you can only expand your expanders through those calls to the expand all functions. You cannot do what match expanders do, which is you can make a match expander that means something in the context of match, but if you use it normally means something else. For instance, when you match lists A, B, C in match, that means a pair of cons pattern matches. But if you write that regular bracket code, it means the actual list function. You can't get that sort of two-sided functionality with generic syntax expanders. For a lot of cases, that's not too much of a problem. For instance, with the command line flags, you're not really ever going to use those outside of command line AC anyway. Now, all of this is making me realize that it's cool. Biggest thing it's taught me is that macros are really complicated. And I'm sure anybody who has read the docs on that giant pile of a syntax system can tell you the same. But it's extraordinarily what we can actually do with it. And the idea of making a base language and then adding in the ways to define extensions to it in a really general way is a very interesting thing that I would like to spend some more work on. And you can do some really, really cool stuff with it and make some very nice special DSLs. That's all I've got. My email is jackhfirth@gmail.com. I am not Jack in the IRC, but I speak through the Slack wormhole, for anyone who's seen that. And I'm Jack Firth on GitHub.
All right, we have time for questions. Yes.
Do you think that it would be useful to have the same syntax expander expand differently in different macro contexts?
Absolutely, and there is some preliminary work in the library in allowing syntax expander types to sort of subtype one another. So you can say, I want this ID to mean this expansion when used in this context, to mean this expansion when used in this one, and to mean this one when not used in any expansion context at all. Can you talk about an example? An example might be making match patterns mean something in syntax parse, in match, and in normal racket all in one go.
All right, anybody else?
On a scale of 1 to 10, how crazy would it be to use your library?
I'd say about, 7, 8 or so. I mean, I won't break it though. I'll just make generic syntax expanders too.
All right, Brian?
So how do you decide where to expand occurrences of your generic expanders in a term? Because, so some things, for example, the macro expander doesn't expand all occurrences of macro keyword followed by stuff. It only expands things in expression positions. And how do you know what the right positions to do expansion are?
There is an explicit check that will, so what happens is when you hit a macro that uses the expand all for expanders or what have you, that function call will just walk the whole syntax tree and look for things that are in expression position and have their first item as a photo expander or something.
But you can't know what expression positions are without doing expansion.
Yes.
Well, yeah, so to think of a concrete example, if you're a match, then that's a call to match.
Oh, hold on.
If the right-hand side of a match is another match with a different match expander, Ryan's point is that you don't want to expand the second one because that's in the second match, not the first one. But I believe that your implementation will expand it as it's expanding the first one, which may be incorrect because of scope, for instance.
in there, would that second match be in the right-hand side of the binding, or would it be in the left-hand side of the match?
It would be in the right-hand side, but it would be within the match parentheses.
Okay, so the general approach there is it's left up to whoever is making the macro that calls the expansion to only call it with pieces of syntax where it's appropriate. For instance, when you do it with match, you wouldn't expand everything in match's body, you would only expand the binding clauses. So I'm not sure if that would get rid of recursion in all cases, but it does for that one.
All right, I think that's time here, but all of our speakers will be available afterwards. No, right, that would be good. All right, our next speaker is Alexis King. And Alexis originally came to Racket because she was interested in developing new languages, and in fact had done so in other languages and found it to be a very difficult and cumbersome process. So she came into Racket and since then has thoroughly absorbed most of the language, including type Racket, and has looked at the sequence situation in Racket and said, we can do better. And so today she's going to present her proposal for generic sequences in Racket.
All right, working. All right, so I'm going to be talking about generic collections. So I'm just going to start off by talking about what are generic collections. That's a pretty easy to answer question for the most part. So I'm actually going to step back and answer what is a collection. This also seems to be a pretty easy question, but it raises some more complicated ones. So for example, obviously the most simple kind of collection in Racket is a list. But collections are anything that hold values. And it turns out that Racket actually has a lot of these built into the standard library. There's a ton of them, and this is great, but nobody uses them. And I think that's a really important point. Why is it that we have all these data structures? Different data structures are obviously way more suited to different tasks. But who here has actually used, say, Racket streams? All right, who here has actually used Racket's growable vectors? All right, so not that many people. And I think that this is indicative of a deeper issue in Racket itself, and in terms of how its libraries are designed. So there are a couple of different reasons that this could be the case. Libraries can't really use anything other than lists, because then everyone has to handle converting them back and forth at every boundary between each library. And the data structures aren't really encouraged by the reference to the guide, but I think these are minor points. I think there are some other issues. Maybe the data structures are mutable, and to do functional programming, we want to have mutable data structures, so that rules out a couple of them. But this still seems pretty good. So why don't they get used? And the answer, in my opinion, is that it's really all about the interfaces that we provide. So if you think about it, there's no vector reverse in the standard library, and that's ridiculous. There's no way to reverse a vector. It's in an SRFI, but we actually discourage that. So obviously, there's not going to be something like group by, which is a great higher order function. It used to be an unstable list, now it's in Racket list, but that's not going to be implemented for anything other than lists, because it's too complicated. Nobody's going to implement it for everything. And just to be clear, sometimes people talk about generic collections, and they think that means that I'm upset about how everything's prefixed with vector. I don't care about that. That's a minor point, and it's the most obvious one, but it's not really the core problem. By the way, as an aside, none of these count in Racket, because all of these things, if you give them immutable vectors, give you mutable ones. But that's a separate problem. So the solution is to have generic collections, and this gives you effectively a uniform interface to every single collection, while keeping the set of primitives small. And what that does is means you can implement a tiny set of functions on any data structure to get the entire library of generic collection operations, including very complicated higher order functions. And they'll just work out of the box. And this makes it very easy to implement new data structures and actually have them be used. So just very quickly, I'm going to go over the primitives. All you have to define, so this is heavily based on Clojure's data structure library. So if you're familiar with that, this is going to look very familiar as well. But so conj is like cons. we add a new element into a collection. Everything's immutable. But we don't make any guarantees about where it goes. So when we conj onto a vector, it goes at the end. When we conj onto a list, it goes at the front. And I guess the actual conj call at the top is chopped off for some reason. But you get the point. If we conj into a set and the element's already in the set, we're going to get back the same set. There's also set nth, which does a functional set at any position. And extend is actually just a quick wrapper around conj. You don't have to implement that yourself, but it takes a collection, another collection, and calls conj on it repeatedly. And this allows us to avoid the problem of creating collections from nothing. So you don't do that. You just give extend in empty, and this lets you convert between collection types if you need to do that. So conj set nth, and then you can choose between implementing first and rest or nth. They're actually implemented in terms of one another. So you only have to write an implementation for one of those two things. Random access is an extra helper. So obviously lists are not random access, vectors are, and that lets the library perform some extra optimizations. And I do that because that basically means that you can implement some optional things, get things to be a little bit faster, and that's true throughout the library. So what's it actually look like? It's pretty much what you would expect. You can use any of the operations. It actually exports bindings that override things from lang-racket. And that's actually okay because if you are using a hash lang and you require a library, bindings will just silently overwrite those. If you're not doing that, you can use trapped in. But the basic idea is it's really straightforward. So you call third on a vector, you get back the third elements. You call set nth on a stream, and you get back a stream. If we convert it to a list, then you can see it's actually there. And there's even generic apply if you're crazy enough to need that for some reason. But also we enforce immutability. So if you give a mutable vector, which again, vectors are mutable by default in Racket if they're not using the reader syntax, then we give a contract error. And because it's really hard to tell when you print out a vector whether or not it's mutable or immutable, I implemented a special contract message that tells you very clearly what the problem is. So it says, expects the sequence, which must be mutable, and was given that vector, which is mutable. So this is all very straightforward. There's nothing super interesting here. But some extra problems come up when you start dealing with the more important functions. So fold is pretty easy. It's probably the simplest, most general higher order function. We can give it anything, and it works. We can even give it disparate collection types. And this is really cool that in Racket and something that supports variadic functions, we can do that. It works. It causes no problems whatsoever. Now, normally, this also applies to some of the other variadic functions, like map. Map on multiple lists works like zip, and it just works generally for any number of lists. But should this return a list or a vector? That's the question now. Exactly. What should this return? Sometimes you don't want a list or a vector. It could, and who knows? So you could say, well, maybe it should return a list because that's the first argument, but that's not a very good answer. So we don't want to actually perform, we don't want to make assumptions for the user of the library. So we don't actually want to create a sequence and return it. We return a continuation that represents the operation to be done. Now this sounds really terrible because now you have this weird continuation thing. No, it's not that. It's just a lazy sequence. So just like enclosure, map, filter, those things are actually going to return lazy sequences. Racket has this built in already. They're called streams. So now if we use map filter on anything, we get back a stream. Now, this is a little bit problematic. Streams do not print out nicely in Racket. Potentially, there could be some improvement done to make them print out in the REPL, maybe force them in the REPL. But for now, this is how they work. But if you convert them to list, you can see that it actually works quite well. Laziness is completely free. We can use it everywhere. And we don't have to litter our code with sequence to list all over the place because all of the general sequence operations work on streams as well. So if we call nth on that stream, we'll actually get back the value. It'll evaluate it up to that point. This is all in Racket stream. I didn't implement any of that. Laziness does allow some kind of fun things. So here's an example where we're mapping over infinite lists. Here's a first example is all the squares. Here's all the Fibonacci numbers. This is actually taken from the Racket homepage. Racket has a lazy language built into it. And using this and using streams, we can actually implement the exact same example just using the main Racket language. Here's a kind of crazy one. There's a randoms function in the standard library that returns an infinite stream of random numbers. You can pass in a random number generator if you want. And so then we can use that in a functional way. And genericism also means that we can be a little bit more efficient because we don't always have to return the exact same type of data structure. So when you reverse a list, that's going to be expensive. Reversing a singly linked list isn't going to be cheap. We just do the reverse. But if you reverse a vector, we don't need to copy the vector because we can just give a view into the vector. It's all immutable, and it'll work fine, as you can see. So the question is this very rackety? So far, this is basically just Clojure's sequence library. And no, but we can make it a lot more rackety. So Racket has a lot of really nice features. One of those is for loops. For loops are great. They basically make it very easy to, I mean, they're not common list loop, but that's probably a good thing. And so, for example, we can use a for loop and just iterate over 5 random numbers, display them out. And this is a side effectful imperative for loop. It works fine. But we can also use something kind of like for list. So for list is like map, but it is a for loop instead. And I use it all the time. I know a lot of people use it all the time. It gives you a little bit more flexibility. So this library provides for sequence. And for sequence is just like for list, but it returns a stream. And that means it is indeed lazy. This is a for loop that returns a lazy stream. So we can use it completely lazily, and we can operate over infinite sequences. So here's the same example from earlier, creating a bunch of squares, but we're using for loop instead. So that all works for free. Is there the potential drawback of, okay, well, side effects are not going to be observed? In the case that you're doing a loop for side effects, you're going to use the regular for loop anyway. So probably not a big problem. And you can also extend this using something called for sequence derived. If you ever use for fold derived, that lets you create custom for loops, which actually this is using. This is very similar, but it lets you, if you create your own data structure, you can create a /your data structure here, and it's very easy in like 2 lines of code. Also, match. So there are match expanders for sequences. And there's actually 3 types, even though they all look pretty similar. So there's the simple one where we just match against a bunch of values. There's a greedy match where we match against basically everything other than the first and last or some other range inside. And there's actually a lazy match. So here we're matching on all the natural numbers, and it still works because the rest of it's not going to get value. And finally, we have contracts. So contracts allow you to put guarantees on absolutely any sequence type, and it'll give you a nice error message as you'd expect. It'll tell you exactly what's wrong and where it came from. So overall, this is using a couple of different facilities in the Racket language that actually, I think, make it a little bit nicer to work with than working with something in Clojure, even though the system is very similar. Partially just because you have much better error reporting and documentation is something I didn't put in here. The Scribble is fantastic, and I've documented all of this API extensively, which you heard work with Clojure, you know, the docs are not really good. So I do want to give a demo. I want to save some time to give a demo, but I was trying to think about what could I demo with a generic collections library, and to a certain extent, you can almost demo anything because you could use this. This is such a general library; it could be used for almost anything at all. But I was thinking instead I'll demo something a little bit different, which is a separate project I did, which implements Clojure's persistent vectors in Racket. And I did not invent these, obviously. They're really cool. I could give an entire talk just on those. But the basic idea is they give you constant time access, constant time functional update, and just really good time guarantees. But they're persistent. You don't have to copy the whole vector every time you change it. Completely immutable. And so this is I'm not going to go through all of this. This is not terribly important. But this is a 260 some line file that implements basically the entire library. But the important part that I want to demonstrate is this bit right here. These are the only methods that I'm implementing. I'm also implementing equality, but specifically representative of my library, I'm implementing length. This is an optional function that, again, allows some optimizations. And I'm implementing conj, I'm implementing nth, set nth, and that random access function. And then some custom framing. And that's it. And now I get the entire complement of Racket's, of the Racket primitives overridden by this library automatically for free, and it works great. So I actually have an example of, it's been a little bit, but This problem came up on the mailing list a couple months ago, and it's a pretty simple problem, but the idea is to implement an algorithm that's like map, but instead of returning a new list, it actually returns n lists. And basically, if you view each list as a matrix, instead the diagonal will be the results of the applications to map. So rather than just having, so I mean, that's probably best demonstrated by an actual application. You can see that basically in the first one, the first element gets mapped over, and the second one, the second element gets mapped over. So it's a pretty simple algorithm, but it turns out it's really slow. And why is it really slow? It's because of this right here. List set is no in operation. And singly linked lists are pervasive throughout Racket, throughout Scheme. They're very simple to define and to understand, but they're not a very good data structure. There's almost always a better data structure to use. So here's the exact same program that does the exact same thing, but it uses persistent vectors. And I just want to demonstrate how almost nothing changed to get this to work. I included my collections library, my p-vector library, and I modified how I'm creating my test sequence. This just uses Racket's range, and I'm basically, this is overridden to return a stream. I'm putting it into a p-vector, and I'm using 4 p-vector instead of 4 lists. And that's it. So how do these actually stack up to each other? Well, when you're running them on small data sets, really small data sets, the list version is going to win every single time. And this is partially because my library is not super well optimized, but also the Racket VM is really good at optimizing list operations. And Racket Generic has a whole lot of indirection that makes this work, because we have to do dispatch and all kinds of things like that. But if we just increase this to 1,000 elements, which really isn't that big, this is not that big a data set, this is tiny, then you'll start to see that because the other algorithms are squared and this one's just n, we win. And if we increase this by just a tiny little bit, double the length, well, basically we're going to win by an order of magnitude. So if that doesn't, if nothing else I said convinced you that these are useful, well, I think they are. And that's why I implemented this. I think this is a pretty good example of why. So there you go. Legitimately a whole order of magnitude better for a very small data set. And again, my library is unoptimized. I use all kinds of things just to make my code pretty, but not necessarily fast. Could do a better job, but this is a good starting point. And I ran it on 10,000 elements just to give you an example. This takes a very long time to run, but you'll see that the list implementation is very, very slow, and the persistent vector implementation is still pretty. It's not great, but it's pretty good. So really, that's about it for me. I just want to mention one more thing before I go that Jack, person right before me, has implemented along with Alex Knaut. Is that how you pronounce your name? Knaut. A lens library, and I have added some. I have a separate library that interacts with that. It's great. I recommend checking it out if you're going to check out these ones as well. Otherwise, that's all I have to say.
All right, we have time for questions.
One thing I like about those data structures is they're actually callable in some ways. So you can call sets as like predicates and maps of functions that are keys and keywords of functions and maps and all that. Is that possible in Racket? Is that something you're interested in?
It's absolutely possible in Racket, and it's actually very easy to do, but it would be implemented on a data structure by data structure basis, most likely. Theoretically, you could build it into the system as a whole. I don't think that necessarily makes a whole lot of sense. But yes, Racket provides a way for making arbitrary structures, procedures, and callable. So you could do something like that. It's probably not as for Racket EDD.
That's what that is, right?
Yeah. Greg Undershot has a library that does that, or a hash line that does that. Raptor.
All right, one more question? All right, Spencer, you're up. So we had a good run, folks, of thinkers who are not PhD students. Unfortunately, we now have one. However, he is not from Indiana University and is therefore not studying in SAM. So Spencer Florence, if I understand correctly, spends most of his time arguing with doctors about why their idea of programs is not actually really feasible. But when I say doctors, I mean physicians, medical doctors. The same could be said for some other doctors, but in this case, it's actually medical doctors. Which explains why he has the urge to just go and write actual programs and useful tools. And so today he's going to be showing us Cover, which is a standalone library for determining code coverage information when you run tests outside of Dr. Racket.
So, last talk, let's do this. So as just mentioned, Cover is a code coverage library for Racket. No one here has played with the code coverage library before. All it does is tell you when your tests aren't running your code, which is something your tests should be doing. This talk is mostly just going to be a demo and me showing off what Cover can do. I'm going to be running Cover the talk on one library I wrote that I just want to plug a little bit because I think it's cool. It's a real library that makes images for Wikipedia. It renders different kind of algorithm, complex Hall algorithms, so that people reading Wikipedia page can actually understand what they're doing. So this is another one from this library. So yeah, this is running on real code. So how does Cover work? Well, so I know some of you use Dr. Racket and probably turned on the built-in code coverage. Unlike that, it's completely separated from the ID. So if we just pop down into our shell where our project is, and just like RacketCon replace RacketCon with Racket Cover, and we can generate a coverage report for the whole project. For those who's running, I'll talk a little bit more about Cover's goals. Cover wants to be an extensible code coverage framework. So what I'm going to show you right now is the HTML output, but you can easily extend it to output to different things. I'll talk a little bit about what those are later in the talk. And also Cover's goal is to run on all the Racket languages, which I'll show you in a bit. But just for starters, the basic coverage view, does not look so good on the screens, looks a little bit like this. We can see that I have been pretty bad about testing this project. We should fix that. So let's see if we can figure out how to get my code coverage up. So this view just shows you all the files in your project and how well they're covered. So you can see that GIF and draw are the worst tested files in this project, and the graphic stuff, so I really don't want to test that. So let's look at the algorithms. So look at the algorithms that I showed you before, using implementations of them. This one's tested pretty well, but this one isn't. So we can drill into a little bit and see, yeah, basically none of this code is tested, except for some stuff at the bottom. Bad me. I shouldn't have done that, so we can fix that. I'm lying, I actually did test it, but this is a state I was in a while back when I was first writing this, where I had not, where I tested for one of them and not the other one, and I just pulled them out into this separate library, or a separate file that will test all of them at once. And now, we can rerun the code coverage, rerun it, there we go. And it will, and you can see that the code coverage will increase. Just for a couple of seconds. But while it's running, I want to point out something else, that this code coverage number is actually a little bit of a lot. This is telling me across all the expressions of my project which ones are covered, but my test files included in that. That doesn't really count, right? You know, if I have 10,000 lines of tests testing 2 lines that don't actually get run, it's going to look like I have good code coverage, but there we go. That's not actually true. So this new number, 67%, isn't right. And so Cover will let you exclude files from your coverage report without actually skipping running. So this -n flag, and say exclude my test directory. And this will run everything in my test directory, but it won't add it to my output. So we'll see that code coverage number go down, hopefully. And this is also true of, say, the infinite RKT, because coverage defines RKT files like RacketTest and sticks them in there. So, it's a little slow. There we go. Now you can see that, yeah, I lost like 5% test coverage. And when we were building cover, we found that we were doing -n tests, -n input RKT, -n scribblings a lot. So cover also comes with this -b flag to just exclude the B is basics. So actually, the reason it's B is kind of interesting. It didn't used to be B, but should we right into the next thing we talked about? Cover tries to support everything that RacketTest supports. So if RacketTest has certain family arguments, we want to offer it. And so it's -B because all the good names are already taken. So, for example, oops, this is a little small. Thanks about that. The RacketTest has a -C flag. Just pick some arbitrary collection and run it. So we can do, let's see how well tested the pick collection is. Pick is kind of big, so it should take a while. So we'll come back to this and see how well libraries actually tested. So cover supports more than just the command line flags from Dr. Racket, from RacketTest. So for example, in the user RKT, RacketTest will find an emit paths option and not run those. Cover will do the same thing, and it also comes with a cover emit paths in case it's something you just want cover to skip. And as of this version, it supports all the new features that RacketTest has, like regular expressions in these and test to include paths, and also I think logical suffixes. So, where was I? Oh yeah. And so I mentioned before that we want the output of cover to be extensible, and so we made some extensions to it. I know who here uses GitHub. Who here uses Travis? Who here would like their code running in Travis to magically generate code coverage for them? Yeah, awesome. So this does that. With this, you can just, once you configure the service called coveralls, which is fairly easy, you can just add one little line to your Travis YAML file and also install this library, and you will get coverage reports shipped right from Travis to coveralls. So you can see that when I did my release, we lost code coverage. I'm not quite sure why that happened. That's not good. And you can add your own coverage format. So if there's some service that you've implemented and you want to play with it, there's this nice API in Cover that will let you create a custom output format, stick it on the package server, and anybody can use it. And hopefully we should actually be releasing a new one of these soon for CodeCub, if anyone wants to use that instead of so that's the basic overview of Cover. But before we go, let's see how well Pick did. So this, it's not under the picked library, but it's under the picked collections. This grabs the tests. Oh, there we go. Coverage index. Let's see how good they are. Yeah, this is partially my fault. I added some tests to this, but more. But yeah, this is one of the cool things with code numbers. You can find that libraries aren't tested and test them. So that's all there is for Cover. Pretty simple library.
All right. All right, questions?
How granular is the exclusion method? If I've got several modules in a file, can I do it that granular, or is it on
So you want to exclude submodules?
Yes.
So Cover actually by default does exclude submodules. And there are flags in the command line for configuring that, so that way your test logicals don't get slipped up with your function sets.
All right, other questions?
Can you say a little bit about how this works? It seems magical. What happened?
Yeah, so unlike the first talk this session, I tried to avoid that because it's pretty ugly in the internals. What it does is it relies on the fact that all Racket languages compile down to the same language, and then it slurps in that language and spits a bunch of annotations across your code that will track when code is run, and then runs the code and collects the results of those annotations. And then does some more crazy hacks to get things working. Like this will now cover macros and things that happen at compile time, which sort of just works by tricking the logging system when communicate across spaces.
Okay, I think I need to ask a follow-up now. Is on a scale from 1 to 10, how crazy is
Completely not crazy at all. I've only found one library it does not work on, and that library is the single most complicated macro in existence. So, yeah, sorry to people who implement type bracket. I can't release the type bracket implementation yet, but everything else works. I know.
Thank you. So I'm sure you wouldn't really use this in, say, production code, but I'm curious. You say you're slurping in a fully expanded code and adding a bunch of annotations. I'm curious how this does, in fact, affect the performance of the code you're doing coverage testing on?
So for code that happens at runtime, I see about a 2 to 3x slowdown. For code that happens at compile time, for reasons I can't explain, it seems to be a little bit worse, maybe 4 times. So if you have something like a very big project, you probably run this asynchronously. So like on the bits of the type representation, this can run on takes like hours.
So given the way that you're sort of, you said like splitting in the program and doing fully expanding code and everything, how do you know that the actual like line counts and expression counts you're getting are the correct ones and it's not some artifact of sort of the expansion process or something like that?
So let me show you something that will answer your question. See how this for loop claims that just this isn't run? It's lying to you, right? Yeah, so the answer to that question is I can't. And this is a bug in the for loops that I have been unable to track down. If you find behavior like this, it is a bug in whoever wrote that macro. And they should go and fix it.
I am a type of verification terrorist. Can you please defend coverage as a meaningful metric of code quality? In particular, coverage is not related to path coverage or related to functional correctness.
You're right, it's not, but we don't have, unless you're writing all your programs in Coq, which I hope you aren't, because, well, that would take a long time to write everything. The metrics we have don't give us a complete picture of, how our code performs. This is one more metric that you can use. You probably want to use more. Like, I would like to add branch coverage and path coverage to this. I just don't quite know what that means in the context of Racket yet. So.
Maybe it's more a metric for your other quality metrics than a metric for the quality of the code itself. It's a metric for the quality of your tests.
Any other questions? All right. Well, thank you, Spencer. And before I hand the microphone back over here, I'd like to have another round of applause and thank you for everyone who helped putting RacketCon together. So Vincent, Asumu, Lee, Matthew, everybody else who helped, the sponsors, excluding me, of course. Please give them a great, great round of applause.
And a big thank you, of course, for all of you for joining us today and making RacketCon, well, what it is. It's a great day where we saw a ton of great talks. Thank you to all the speakers.
thank you for all the audience and all the great interactions, all the great conversations. It's just great to see all the Racket community come together, just have a great time together. It's the biggest party of the year, at least in the Racket community, and we're all very happy that you're here. So thank you all for coming, and I invite you next year for RacketCon, 6th RacketCon. Thank you very much.